What if everything around us, the stars in the night sky, the cells in our bodies, the very fabric of space and time wasn't just the result of random chance, but part of a grand, self-directed cosmic construction project? Imagine looking up at the heavens and realizing that the universe isn't simply expanding into emptiness, but actively building itself, moment by moment, through intricate and deeply woven patterns. It's as though reality itself is an architect, working from a set of hidden blueprints written into the laws of physics, mathematics, and emergence. This idea might sound like science fiction, but it's a breathtaking reality that modern science is only beginning to unravel, and it invites us to see the cosmos in a completely new light. From the very smallest scales, where quantum particles flicker in and out of existence, to the largest structures we can observe, galactic superclusters arranged like neurons in a cosmic brain, the universe seems to follow a rhythm. A silent, elegant order emerges from what appears at first glance to be chaos. We'll explore how simple rules give rise to astonishing complexity, how symmetry and broken symmetry shape the diversity of matter, and how principles like entropy and feedback loops don't just lead to disorder. They actively create the conditions for stars, planets, and even life itself to come into being. This isn't a story of randomness. It's a story of a universe that knows how to build, how to grow, and how to evolve in ways that are both mathematically precise and creatively profound. By the end of our journey together, you won't just see the cosmos as a beautiful accident. You'll recognize it as a masterpiece of self-organization, a dynamic, interconnected system where patterns repeat across scales, from the branching of trees to the spiraling of galaxies. We're going to dive deep into the forces that shape reality, and along the way, you might just rethink everything you thought you knew about order, chaos, and our place within it all. So settle in, open your mind, and get ready to explore how the universe builds itself, and perhaps in doing so, discover something new about how we ourselves are woven into its ever-unfolding story. So what does it mean for the universe to possess a blueprint? It's not a physical set of plans tucked away in some cosmic vault. Rather, it's an innate, built-in capacity for order to spontaneously arise from seemingly random interactions. This is the profound concept of self-organization, the universe's ability to architect its own complexity without any external designer calling the shots. Think about the intricate, swirling patterns of a galaxy. It wasn't assembled by some celestial hand. Instead, it emerged from the simple, relentless pull of gravity acting on countless particles of dust and gas, each following a basic rule of attraction. From the chaos of a primordial cloud, a magnificent, structured spiral gracefully coalesces. This process isn't a rare exception. It's the fundamental way our cosmos operates, from the very small to the unimaginably large. We can see this principle at work all around us, even right here on Earth. Consider a termite mound, an astonishingly complex structure with arches, tunnels, and ventilation systems that maintain a perfect internal climate. No single termite holds the architectural plans. Each insect is just following a simple set of instinctive behaviors, responding to local cues like the pheromones left by others and the density of the dirt around them. Out of these countless micro-interactions, a magnificent macrostructure emerges. It's the same story at the molecular level. Atoms, mindlessly obeying the laws of electromagnetism, link together to form molecules, which then self-assemble into proteins, cells, and eventually, conscious beings capable of wondering how it all happened. The transition from simplicity to complexity is a universal theme. The engines driving this incredible self-assembly are a set of powerful, interlocking principles. First are feedback loops, which act like the universe's quality control and amplification system. In a positive feedback loop, an effect reinforces its own cause, leading to exponential growth or change. Imagine a sound microphone picking up its own output from a speaker, creating that familiar, escalating screech. In the cosmos, this is how a slight overdensity in a cloud of gas can have a runaway effect. Gravity pulls more gas in, which increases the density, which pulls in even more gas, and so on. Conversely, negative feedback loops provide stability and balance. They dampen fluctuations, keeping a system within sustainable bounds. Your body's ability to regulate its temperature is a perfect example of negative feedback, maintaining a delicate equilibrium. Then there are nonlinear dynamics, which tell us that in complex systems, cause and effect are not always proportional. A small, seemingly insignificant nudge can sometimes trigger a massive, unpredictable outcome, the famous butterfly effect. This nonlinearity is why weather is so difficult to forecast beyond a few days, and why the universe is so creative and diverse in its formations. It means you can't always predict the magnificent end result just by knowing the starting rules. Finally, we have the concept of criticality, that precise, knife-edge state between stability and chaos where systems are primed for change. It's like a pile of sand where adding one more grain causes a cascade of avalanches. The universe seems to love operating near these critical points, where it is most adaptable and where new patterns can erupt into existence most easily. Perhaps the most stunning example of these principles in action is the birth of a star. It begins in a cold, dark, and chaotic molecular cloud, a vast and seemingly disordered region of space. But within that cloud, tiny fluctuations in density create slight gravitational advantages. These areas begin to pull in more matter, a positive feedback loop that starts to carve out a dense core. As this core collapses under its own weight, pressure and temperature skyrocket in a nonlinear fashion. They don't just increase gradually. They explode to millions of degrees, crossing a critical threshold where nuclear fusion ignites. Suddenly, a new sun is shining. The local interactions of countless particles, all governed by simple physical laws, have given rise to a brilliant, global structure that will light up the cosmos for billions of years. This is the cosmic blueprint in its most glorious form, revealing a universe that is not a static artifact but a dynamic, self-assembling masterpiece, building its grandeur from the ground up. Now, if self-organization is the universe's innate architectural talent, then symmetry is the fundamental design principle it follows. Think of symmetry not just as a beautiful, balanced shape, like a butterfly's wings or a snowflake's perfect form, but as a deep, underlying rule that grants the cosmos its stability and predictability. At its heart, a physical symmetry means that a law of nature remains unchanged under a transformation. For instance, the fact that the law of gravity works the same today as it did a billion years ago is a symmetry in time. The principle that momentum is conserved, that the total momentum in a system remains constant unless acted upon by an outside force, is a symmetry of space itself. These aren't just abstract ideas. They are the unwavering pillars that hold reality together, providing a consistent and reliable framework upon which everything else can be built. Without these fundamental symmetries, the universe would be a chaotic, lawless place where prediction would be impossible, and complexity could never take root. But here's the truly fascinating twist. If symmetry alone ruled, our universe would be a perfectly balanced, uniform, and frankly boring place, a featureless sea of sameness. The real magic, the spark that ignites the creation of everything we see, is when this perfect symmetry is broken. This moment of breaking is not a flaw or a mistake. It is the essential creative act that allows diversity and structure to burst into existence. Picture a perfectly calm, frozen lake on a cold morning. Its surface is a vast, uniform, and symmetrical sheet of ice. Now, as the temperature changes, that ice begins to crack. The perfect symmetry of the smooth surface is shattered, and in its place, a unique and intricate web of fissures and patterns emerges. That cracking is symmetry breaking. The uniform potential of the ice gives way to a specific, complex reality of lines and fragments. This is precisely what happened in the earliest moments of our universe. Immediately after the Big Bang, the cosmos was an unimaginably hot, dense, and perfectly symmetrical state. The fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were unified into a single superforce. There was no distinction between matter and antimatter. But as the universe expanded and cooled, it underwent a series of dramatic phase transitions, much like steam condensing into water or water freezing into ice. At each critical juncture, a symmetry was broken. The single unified force fractured into the distinct forces we now observe. In one of the most crucial breaks, a slight asymmetry favored matter over antimatter. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. After they annihilated each other, that 1 in a billion leftover was all the raw material that would eventually form every galaxy, star, planet, and person. This tiny imperfection, this broken symmetry, is the sole reason anything exists at all. This principle of broken symmetry echoes through every scale of reality. It's the reason we have different types of particles with varying masses and properties. It's the mechanism that gives particles mass in the first place, through the Higgs field, a field that permeates all of space and whose broken symmetry allows some particles to interact with it heavily while others glide through unaffected. This same process of symmetry breaking is even at work in the development of life itself. A fertilized egg is initially symmetrical, but as it divides, chemical gradients and signals break that symmetry, determining which cells become part of the head and which become part of the tail, orchestrating the emergence of a complex, asymmetrical organism from a simple, uniform beginning. This shows us that asymmetry and imperfection are not signs of error. They are the signature of a universe that is dynamic, creative, and evolving. The cosmos builds its incredible complexity not through rigid perfection, but through a beautiful, generative dance between balance and imbalance. So from the cosmic dance of symmetry and its breaking, we move to another breathtaking act of self-assembly, one where the whole becomes something far greater than the sum of its parts. This is the principle of emergence, the astonishing phenomenon where simple, mindless components, following basic rules, interact to produce complex, intelligent, and entirely unexpected behaviors that simply do not exist in the individual pieces. Think of a single neuron in your brain. On its own, it's just a specialized cell, firing electrochemical signals. It doesn't have thoughts, feelings, or memories. But when you gather billions of them, connecting them in an unfathomably complex network, something miraculous happens. From that collective activity, consciousness itself emerges. The ability to experience the color red, to feel love, to wonder about the universe. The wet, physical stuff of the brain gives rise to the intangible experience of the mind, a new layer of reality that cannot be predicted by studying a single neuron in isolation. We see this magic of emergence everywhere we look in nature. Consider a flock of starlings weaving through the sky in a mesmerizing, swirling cloud called a murmuration. There is no lead bird choreographing this aerial ballet. Each bird is just following a few simple local rules. Stay close to your neighbors, avoid collisions, and match their general direction. Out of these countless individual decisions, the entire flock moves as a single, fluid superorganism, creating shapes and patterns that are beautiful, complex, and seemingly intelligent. It's a property of the group, not the individual. The same thing happens in an ant colony. A single ant has a limited repertoire of behaviors, but the colony as a whole can farm fungi, wage intricate wars, and build elaborate, climate-controlled cities. The colony has an intelligence and a capability that emerges only from the interactions of its many simple members. This process of emergence is how the universe builds itself in layers, creating a hierarchy of complexity where each new level enables the next. It's a foundational architecture of reality. Start at the very bottom with subatomic particles. They organize to form atoms. Those atoms then bond through electromagnetic forces to create molecules, a new level with new properties, like the ability to form complex chains. Those molecules, like proteins and lipids, can then self-assemble into cells, the fundamental units of life. This is a monumental leap. A living cell has capabilities that its constituent molecules do not. It can metabolize, reproduce, and respond to its environment. Groups of cells then specialize and collaborate to form tissues, organs, and eventually, entire organisms. And from the social interactions of conscious organisms, cultures, economies, and technologies emerge. Each tier rests upon the one below it, but operates with its own set of rules and behaviors that cannot be reduced or explained away by the lower level alone. A psychologist studying human emotion doesn't need to constantly refer to quantum field theory, because the level of consciousness has its own emergent laws. This reveals a cosmos that is not just built linearly, but is instead a nested set of patterns within patterns, a fractal-like architecture of reality. The universe is fundamentally creative, using simple rules as building blocks to bootstrap itself into ever greater sophistication. The laws of physics govern particles, which enable chemistry, which enables biology, which enables psychology, and so on. Each emergent layer is a new domain of existence with novel properties and potentials. And this isn't just a terrestrial affair. We can look out into the cosmos and see this same hierarchical organization at a grand scale. Stars emerge from clouds of gas, then group into galaxies. Those galaxies gravitationally bind into clusters, and those clusters into vast filaments that make up the cosmic web, the largest known structure in the universe. This web, with its nodes and voids, looks uncannily like a neural network in a gigantic brain, hinting that the principle of emergence might operate on the absolute grandest of scales. By understanding this, we begin to see the universe not as a random collection of stuff, but as a coherent, self-assembling whole, constantly building upwards and outwards into new forms of complexity and beauty. Now, if emergence shows us how complexity arises from simplicity, then entropy introduces us to the universe's most misunderstood and powerful creative partner, the arrow of time. We often think of entropy as the great destroyer, the inevitable slide into disorder and decay, the reason ice melts in your drink, why your room gets messy, and why all things eventually fall apart. This is the classical view, and it's not wrong, but it's only half the story. In reality, entropy is far more than just a measure of chaos. It is a fundamental driving force for self-organization, a relentless push that actually guides systems toward states of higher probability, complexity, and even beauty. To see entropy as only a force of destruction is to miss its profound role as a cosmic architect. This creative power of entropy becomes clear when we watch energy flow through a system. Think about a pot of water sitting on a stove. When you first turn on the heat, the water is still and uniform, but as heat energy, a form of disordered energy, is pumped in from the bottom, that energy needs to be dissipated. It can't just sit there. The water begins to organize itself into elegant, rolling convection cells. Hot water, being less dense, rises to the surface, cools down, and then sinks back down to be reheated. This creates a beautiful, structured pattern of circulation, a dynamic order that exists solely to spread out the incoming energy more efficiently. The system has actively used the flow of energy to create a complex, organized structure. This is entropy in action, not as decay, but as a formative process. We see this same principle on a planetary scale in our weather systems. The immense energy Earth receives from the Sun is incredibly ordered, arriving as beams of light. Our atmosphere and oceans work to dissipate this energy, and in doing so, they self-organize into the vast, swirling patterns of hurricanes, jet streams, and ocean currents. Without the drive to increase entropy, we would have no weather at all, just a stagnant, lifeless ball. This irreversible process of energy dispersion is what gives us the arrow of time, the one-way direction from past to future that we all experience. The universe began in a state of incredibly low entropy right after the Big Bang, a remarkably ordered, dense, and hot state. Since that moment, the total entropy of the cosmos has been steadily increasing, and it is this increase that provides the temporal scaffolding upon which cosmic evolution is built. Time has a direction because entropy has a preferred direction. This isn't just a philosophical point, it's the engine of history. The early universe was a smooth, almost featureless soup of particles. As it expanded and cooled, and as entropy increased, gradients were created, differences in temperature, density, and pressure. And it is across these gradients that energy flows, and it is this flow that powers the formation of every complex structure we see. Stars, galaxies, planets, and life itself are all beautiful, temporary eddies in this vast, cosmic river of increasing entropy. A simple analogy can help reframe our intuition. Consider a child building a sandcastle on the beach. From one perspective, the story of the sandcastle is a classic tale of entropy. The wind and waves will eventually erode it, scattering the sand grains back into a disordered state. The organized structure succumbs to disorder, but that's only the final chapter. To build the sandcastle in the first place required a tremendous flow of energy. The child had to expend energy to gather the sand, shape it, and design it. That energy was dissipated as heat from the child's body and as the sound of their laughter. The sandcastle itself is a product of that energy dissipation. It is a localized pocket of order that was created at the cost of increasing the overall entropy of the universe. The castle's formation and its dissolution are two parts of a single entropic process. This shows us that order and disorder are not opposites. They are deeply intertwined partners in a cosmic dance. The universe doesn't choose between them. It uses the relentless drive toward disorder to fuel the creation of exquisite, temporary order. This principle completely revolutionizes our view of reality. It challenges us to see the universe not as a static object slowly winding down, but as a dynamic, far from equilibrium system where the flow of energy and the increase in entropy are the very things that fuel creation. The emergence of galaxies, the intricate chemistry of life, and the spark of consciousness are not accidents that occur in spite of the second law of thermodynamics. They are direct consequences of it. They are the magnificent and complex ways that the universe finds to disperse energy and increase entropy over billions of years. Our existence is a testament to the universe's incredible capacity to build breathtaking structures out of its own inevitable journey toward disorder. So if entropy provides the directional flow that powers cosmic construction, then feedback loops are the ingenious control systems that regulate this entire process, ensuring that the universe's creativity doesn't spiral into chaos or grind to a halt. At its core, a feedback loop is a simple but profound concept. It's a circular chain of cause and effect where the output of a system circles back to influence its own input. This self-referential mechanism acts as the universe's built-in governance, a way for complex systems to monitor and adjust their own behavior from within, without any need for an external manager. It's the principle that allows for both explosive growth and delicate balance, and it's absolutely everywhere we look, from the biology in our bodies to the grandest structures in the cosmos. We can break these loops down into two fundamental types that often work in tandem: positive and negative feedback. Positive feedback is the universe's amplifier. It takes a small change and magnifies it, creating a runaway effect that drives a system toward a dramatic new state. Think of the sound of a microphone feeding back into a speaker. That initial whisper gets picked up, amplified, and played back louder, which is then picked up again and made louder still, rapidly escalating into an ear-splitting screech. In the natural world, this is the engine of transformation. The birth of a star, which we touched on earlier, is a classic cosmic example. A tiny, random fluctuation in a gas cloud creates a slightly denser region. Gravity, acting as a positive feedback loop, pulls more gas toward that density. This makes the region even denser, which strengthens the gravitational pull, attracting even more gas in a powerful, self-reinforcing cycle that culminates in the ignition of a new sun. It's a process that takes a minor imperfection and builds a brilliant, lasting structure from it. On the flip side, we have negative feedback, the great stabilizer. This is the universe's thermostat. Its job is to dampen fluctuations, counteract deviations, and maintain a system in a state of equilibrium or homeostasis. A perfect example is your own body's ability to regulate its internal temperature. If you start to get too hot, your body responds by dilating blood vessels and producing sweat, which cools you down. If you get too cold, it constricts blood vessels and induces shivering to generate heat. The output, your body temperature, feeds back to trigger responses that oppose the initial change, keeping you within the narrow, vital range necessary for survival. On a planetary scale, Earth's climate system is riddled with negative feedback loops. For instance, if global temperatures rise, it can lead to more evaporation from the oceans and increased cloud cover. Those brighter, white clouds reflect more of the sun's energy back into space, which has a cooling effect that counteracts the initial warming. This balancing act is crucial for maintaining the stable conditions that allow planetary systems to thrive. Now, let's scale this up to a truly cosmic level. Consider the majestic spiral galaxy, a structure that must remain stable for billions of years to allow stars like our Sun to form and nurture planets. This incredible longevity isn't a given. It's actively maintained by a gravitational feedback loop involving an invisible player, dark matter. Every galaxy is thought to be embedded within a vast, diffuse sphere of this mysterious substance called a dark matter halo. The gravity from this halo provides a crucial stabilizing influence. As stars and gas clouds within the galaxy orbit the center, their own gravity would tend to make the galactic disk unstable and prone to flying apart or collapsing over time. But the immense gravitational pull of the dark matter halo acts as a regulating force, a form of negative feedback that keeps the visible matter in check, providing a steady gravitational scaffold that allows the galaxy to maintain its structure across eons. This stability is what provides the calm, long-term environment necessary for the positive feedback of star formation to occur within the galactic clouds, once again showing how these two types of loops work together. This dynamic interplay between the amplifier and the stabilizer is what gives the universe its resilience and adaptability. Positive feedback loops provide the drive for change, innovation, and the creation of new structures. They are the source of exponential growth and phase transitions. Negative feedback loops provide the memory and the stability, allowing those new structures to persist long enough to become platforms for the next level of complexity. They allow systems to absorb shocks and perturbations like a gravitational wave from a distant collision or the influx of new material without completely disintegrating. A system that is all positive feedback would explode violently out of control. A system that is all negative feedback would be frozen in stasis, incapable of change or evolution. But the universe, in its profound wisdom, uses both. It's this constant, dynamic dance between reinforcing and balancing forces that crafts the stable yet evolving architectures we see throughout the cosmos. From the delicate balance of a solar system to the enduring structure of a galaxy cluster, proving that the universe is not a static sculpture, but a living, breathing, self-correcting system. But now, we must venture into a realm where the universe's straightforward rules reveal a surprising twist. A domain where predictability gives way to a more creative and intricate kind of order. This is the world of nonlinear dynamics, a branch of mathematics and physics that deals with systems where cause and effect are not neat, proportional, or easily predictable. In a linear system, you might expect that doubling the effort would double the result, push a swing twice as hard, and it goes twice as high. But the universe is overwhelmingly nonlinear. Here, a tiny, almost imperceptible nudge can sometimes unleash a tidal wave of change, while a massive shove might have surprisingly little effect. This inherent nonlinearity is what makes our cosmos so rich, so diverse, and so beautifully unpredictable. It's the reason why we can't forecast the weather perfectly beyond a week. And it's the very engine that allows for the spontaneous emergence of complex patterns from simple rules. This fascinating field is intimately connected to chaos theory, which is perhaps one of the most misunderstood concepts in all of science. Chaos does not mean pure, lawless randomness. Instead, chaos theory reveals how completely deterministic systems governed by precise, knowable laws with no element of chance, can still produce behavior that appears utterly complex and random. The equations are fixed, but the outcomes are exquisitely sensitive to their starting conditions. This is the famous butterfly effect, a powerful metaphor coined by meteorologist Edward Lorenz. The idea is that the delicate air disturbance from a butterfly flapping its wings in Brazil could set off a chain of escalating atmospheric events that ultimately influences the formation of a tornado in Texas weeks later. The flap itself doesn't cause the tornado, but it can be the tiny initial push that alters the system's path toward that outcome instead of another. It's a stunning demonstration of how the universe is so interconnected that the smallest of actions can ripple across vast scales of space and time. We can extend this profound idea all the way back to the origin of everything. In the first fleeting moments after the Big Bang, the universe was a seething quantum foam, a realm of fundamental uncertainty and constant fluctuation. At this scale, virtual particles flickered in and out of existence, creating microscopic wrinkles in the fabric of space-time. According to inflationary cosmology, these quantum fluctuations were not smoothed away. Instead, the rapid exponential expansion of the universe in its first fraction of a second stretched these tiny, subatomic wrinkles to astronomical sizes. Those infinitesimal seeds of unevenness, born from quantum chaos, became the gravitational wells that eventually attracted matter. Over billions of years, they grew into the vast cosmic web of galaxy clusters and immense voids that we observe today. The entire large-scale structure of our universe, with its magnificent filaments and nodes, may ultimately be a fossilized imprint of primeval quantum chaos, a permanent structure built upon a foundation of microscopic uncertainty. Yet, within this seemingly unpredictable chaos, there is a deep and comforting form of order. Chaotic systems often evolve toward what mathematicians call attractors. An attractor is a preferred state or a set of states that a system naturally settles into over time, a kind of behavioral magnet. Think of water swirling down a drain. No matter how you disturb it, the flow will always organize itself into a characteristic spiral pattern. That spiral is its attractor. In the cosmos, we see this everywhere. The planets in our solar system have settled into rhythmic, regular orbits around the Sun, cyclic attractors that have persisted for billions of years. Even the expansion of the universe itself may follow a pattern toward a specific attractor state, perhaps a final fate of maximum entropy or a cyclic model of eternal return. These attractors show that chaos doesn't lead to formless anarchy. It leads to a bounded, patterned form of disorder. It's a strange dichotomy where the system's long-term future is predictable in its general shape, its attractor, while its precise moment-to-moment behavior remains forever unpredictable. This reveals the ultimate creative power of this principle. The universe's self-organization doesn't happen in a placid, steady state. It thrives on the edge of chaos, in that dynamic and fertile zone between rigid order and total disorder. It is at this boundary that systems are most adaptable, most innovative, and most capable of generating new forms of complexity. A system that is too ordered becomes brittle and static, unable to adapt to change. A system that is too chaotic is formless and incoherent. But a system poised at the edge of chaos has the flexibility to explore new possibilities and the stability to retain successful innovations. This is how evolution works, exploring genetic possibilities. It's how our brains work, with neural networks balancing stability and plasticity. And it appears to be how the cosmos itself builds its structures, using the creative tension between deterministic laws and chaotic dynamics to weave a tapestry of incredible diversity and beauty. The universe is not a clockwork mechanism. It is a dynamic, living process that dances on the razor's edge, and it is in this dance that all things are made new. But just as chaos theory reveals the hidden order within apparent randomness, there's another breathtaking principle that shows us how the universe reuses its most successful designs, crafting a world where the patterns of the very small echo perfectly in the very large. This is the concept of scale invariance, the remarkable property where a pattern or process looks exactly the same or very similar, no matter how much you zoom in or zoom out. It's as if the cosmos has a set of favorite blueprints that it uses over and over again, from the infinitesimal to the astronomical, suggesting a deep and universal architectural style governing all of reality. This isn't about things being identical in size, but about their form and structure being recapitulated across vastly different dimensions, hinting at a common set of physical rules that operate seamlessly across every level of existence. The most beautiful and mind-bending manifestation of this principle is found in fractal geometry. A fractal is a shape that is infinitely complex and self-similar, meaning that as you look closer and closer, you keep finding smaller copies of the overall pattern nested within itself. Think of a mighty oak tree. From a distance you see its broad shape. Move closer, and you see that each major branch splits into smaller branches in a similar way. Closer still, and each twig replicates that same branching pattern. And if you could look at the veins in a single leaf, you'd find that they too form a miniature version of the tree's entire structure. This isn't a perfect replica at every scale, but the core pattern repeats, a signature form that the tree uses to build itself from its massive trunk down to its microscopic vascular system. This efficient, repetitive design allows the tree to maximize its surface area for gathering sunlight and exchanging gases. An elegant solution engineered by evolution that mirrors the universe's own methods. We are literally surrounded by these fractal forms in the natural world. Look at a snowflake forming in a cloud. The same crystalline branching pattern dictates its growth from a single water molecule to a complex, six-sided stellar dendrite. Observe a river delta from an airplane window. The main channel splits into smaller tributaries, which split again into even smaller streams, creating a pattern that looks strikingly similar whether you're looking at the massive Mississippi Delta or a tiny trickle of water carving through mud after a rainstorm. Even the very air we breathe is filled with turbulence, the chaotic flow of fluids and gases, which organizes itself into swirling eddies that contain smaller eddies, which in turn contain even smaller ones, a cascading fractal dance that dissipates energy across multiple scales. These aren't just happy accidents. They are the inevitable outcomes of physical processes seeking the most efficient pathways, whether for electrical discharge in a lightning bolt, for the flow of water, or for the transfer of energy. And this principle doesn't stop at our planet's atmosphere. It extends out to the very fabric of the cosmos itself. When cosmologists began mapping the universe in 3 dimensions, they made an astonishing discovery. Galaxies are not scattered randomly through space like raisins in a pudding. Instead, they are arranged in a vast cosmic web, an immense network of long, thin filaments of galaxies interspersed with enormous empty voids. This structure, the largest we know of, is profoundly fractal. The filaments themselves are not smooth rivers of stars. If you zoom in on one, you'll find that it is made of clusters of galaxies. Zoom in further on a cluster, and it's made of individual galaxies. Zoom into a galaxy, and you find it has a fractal structure of spiral arms, which are made of star clusters, which are made of stars, and so on. The distribution of matter across the universe, from hundreds of millions of light years across down to the scale of a single solar system, exhibits this self-similar, hierarchical clustering. It appears the universe itself is constructed as a fractal. This incredible scalability points to a profound underlying truth. The universe seems to build itself using a common and incredibly efficient set of geometric and dynamic templates. A simple mathematical formula, when iterated over and over again, can generate the infinitely complex and beautiful shape of the Mandelbrot set, a kind of master fractal that contains endless patterns within its boundary. In a very similar way, simple physical rules, like gravity acting on dark matter or the laws of hydrodynamics, when set in motion and allowed to play out over billions of years, iteratively build the cosmic web without any need for a grand designer. It's a process of spontaneous self-organization where complexity emerges from the relentless application of basic laws. This fractal architecture is not just beautiful, it's supremely functional. It allows for efficient connectivity, maximizing gravitational influence and the flow of matter across the universe, and it creates an incredible amount of surface area, the interfaces between filaments and voids, where the dynamic action of star formation and galactic evolution is most intense. Recognizing this pattern allows us to see the cosmos in a radically new light. It's not a collection of separate, unrelated objects, but a coherent, unified whole where every part reflects the whole. A galaxy is not an island universe. It is a node in a cosmic network that looks the same in its essential structure, whether you are looking at a patch of space the size of your neighborhood or the entire observable universe. This fractal view suggests a deep unity in the laws of physics, a consistency that allows the same patterns to emerge regardless of scale. It hints that the universe might be fundamentally woven from a common thread, a geometric and dynamic principle that repeats itself eternally, building a reality that is both endlessly diverse and elegantly simple in its underlying design. Now, just as nonlinear dynamics and fractals show us how patterns repeat and chaos breeds creativity, the universe also has a flair for the dramatic. It builds itself through sudden, explosive transformations, moments where everything changes all at once in a grand, collective shift. These are phase transitions, the cosmic equivalent of a caterpillar dissolving in its chrysalis only to reorganize itself into a butterfly. We see them every day. Water, when heated enough, doesn't just get warmer gradually. It undergoes a radical transformation, violently churning into a new state of being as steam. Apply cold, and those freely moving molecules suddenly lock into the rigid, crystalline architecture of ice. These aren't just simple changes. They are profound reorganizations of matter, moments where a system collectively chooses a new way to be, driven by changes in energy and pressure. And this isn't just a kitchen phenomenon. It's a fundamental engine of cosmic construction, a powerful mechanism of self-organization where simplicity gives way to complexity in a sudden, spectacular leap. What's truly fascinating is that these transitions are the ultimate team effort. They are emergent phenomena in their purest form. Think about a crowd at a concert. For a while, everyone is clapping out of sync, a disorganized noise. Then, almost magically, a rhythm emerges. One person isn't directing it. It's a spontaneous, collective decision made by the entire crowd acting as one system. A phase transition works the same way. When you cool a magnet, for instance, there's a specific critical temperature where something incredible happens. Above that temperature, all the tiny atomic magnets are pointing in random directions, their magnetic fields canceling each other out. The material has no overall magnetism. But as it cools past that critical point, it's as if a silent command sweeps through the entire structure. Neighboring atoms influence each other, and suddenly, vast domains of atoms spontaneously align in the same direction. The material, as a whole, becomes magnetic. This shift isn't gradual. It's a sudden, system-wide flip into a new, highly ordered state. A perfect example of how local interactions can lead to a dramatic global change without any external manager. This concept of a tipping point, that precise moment of transformation, is known as criticality. It's the knife-edge state between two phases of matter, the moment of maximum potential where a system is poised between stability and chaos, between order and disorder. It is at this critical point that systems become exquisitely sensitive and incredibly creative. A classic example is a pile of sand. As you add grains one by one, the pile grows steadily. But there comes a point where the slope is so steep that adding one more grain doesn't just sit on top. It triggers an avalanche that reshapes the entire slope. That pile is at criticality. It's primed for change. This state is found throughout nature. In the forests, the arrangement of trees can reach a critical state where a single lightning strike can lead to a runaway cascade, a wildfire that rapidly spreads and resets the entire ecosystem. Even our own brains are thought to operate near criticality, with neural networks balanced perfectly between a silent, orderly state and a chaotic, seizure-like frenzy. In this poised state, the brain has the maximum capacity for processing information, adapting to new stimuli, and generating creative thoughts. It is at the edge of chaos that innovation thrives. And we can trace this powerful principle of criticality and phase transitions all the way back to the origin of everything. The early universe was a sequence of the most dramatic phase transitions imaginable. Immediately after the Big Bang, the cosmos was an indescribably hot, dense soup where the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces, were unified into a single super force. As the universe expanded and cooled, it crossed critical temperature thresholds. At each one, a symmetry was broken, and a force peeled away from the others in a cosmic phase transition of unimaginable scale. The most significant of these for our existence happened around 380,000 years after the beginning. Before this, the universe was a searing, opaque plasma, so dense that light particles, photons, were constantly scattered by free electrons trapped in a hot fog. But as the temperature dropped below a critical point of about 3,000 Kelvin, electrons could suddenly combine with protons to form the first stable hydrogen atoms. This event, known as recombination, was a universe-wide phase transition. In an instant, the opaque plasma cleared, and photons were suddenly set free to travel across space. This flash of light, stretched by 13.8 billion years of expansion, is what we now detect as the cosmic microwave background radiation, the afterglow of the Big Bang and the oldest light in the universe. That single critical moment gave us a transparent cosmos and the first building blocks of matter, atoms, setting the stage for everything to come. This shows us that the universe doesn't always build itself slowly and incrementally. Some of its most important work is done in sudden, revolutionary jumps. These critical transitions are the universe's way of unlocking new levels of complexity. Each phase transition opened up new possibilities. The separation of forces allowed for different types of interactions. The formation of atoms allowed gravity to begin pulling matter into clouds that would become galaxies and stars. And inside those stars, further phase transitions of nuclear fusion would forge the heavier elements necessary for planets and life. The cosmos builds itself through these dramatic, threshold-crossing events. Moments of creative destruction where the old order dissolves to make way for the new. It's a story of punctuated equilibrium on a grand scale. Long periods of steady evolution interrupted by brief, violent explosions of change that redefine the entire system and unleash new potentials, crafting a universe that is forever evolving and ascending to new forms of structure and beauty. So if the universe builds itself through dramatic leaps and collective shifts, it also constructs its most enduring structures through the silent, steady power of connection. This brings us to a principle that might feel modern, but is in fact as ancient as the cosmos itself: network theory. At its heart, this is the science of relationships. It posits that what truly defines a system, be it a cell, a society, or a galaxy, is not just the individual components, but the intricate web of connections between them. Every node, whether it's a person, a star, or a neuron, gains its power and purpose from its links to others. This perspective reveals that the universe is fundamentally a vast, multi-layered network, and its incredible resilience, efficiency, and creativity arise directly from this interconnected architecture. One of the most fascinating properties to emerge from this study is the concept of the small world network. This is the idea that any two nodes in a vast system can be connected by a surprisingly small number of steps. You've likely experienced this in social settings, the famous 6 degrees of separation concept, where you might be only a handful of introductions away from anyone else on the planet. This isn't magic. It's a mathematical property of how certain networks organize themselves. They achieve this through a mix of highly connected hubs and long-range weak ties that bridge distant clusters. This architecture allows for the incredibly rapid flow of information, energy, or influence. A rumor can spread like wildfire through a social network. An electrical signal can flash through your brain, or a gravitational disturbance can propagate through a galaxy cluster, all because of this efficient, small world design. And we find this same structural elegance woven into the largest thing we can possibly observe, the cosmic web. This isn't just a pretty name, it's a literal description. Galaxies are not isolated islands in space. They are strung together along immense, gossamer filaments of dark matter and gas, intersecting at dense nodes to form colossal clusters. These filaments act as the highways of the universe, guiding the flow of matter and energy. What's truly breathtaking is that this vast web, spanning billions of light years, exhibits the very same small world property. A galaxy on one side of a void can be gravitationally linked to a cluster on the other side through a relatively short chain of interactions along these filaments. This connectivity allows influences to travel and structures to form in a coordinated way across mind-boggling distances, proving that the universe is a deeply interconnected whole. This profound connectivity is the source of a system's greatest strength: resilience. Think about the Internet. It was originally designed for military purposes to withstand a nuclear attack. The idea was that if one node or connection was destroyed, information could simply reroute itself through countless other pathways. The network has no central command that would be a single point of failure. Its power is distributed. We see this same robust design in natural ecosystems. A healthy forest has a complex food web with many different species. If one species declines, others can often fill its ecological role, preventing the entire system from collapsing. The connections provide redundancy and flexibility. Now, apply this to our cosmic web. The gravitational connections between galaxies and clusters create a stable, resilient structure. While individual stars may be born and die, the larger network persists for billions of years, providing a stable scaffolding for cosmic evolution. It can absorb shocks like galaxy collisions and reconfigure itself without coming apart. But networks aren't just about stability. They are also the ultimate engines of innovation. When diverse nodes are connected, the potential for novel interactions skyrockets. Your brain is the quintessential example. Your creativity, your memories, your very consciousness do not live in any single neuron. They emerge from the ceaseless, dynamic conversation between billions of them. Each new connection strengthens some pathways and weakens others, allowing you to learn, adapt, and create. This is how innovation works on a societal level too. Cities are hubs of human networking, where the collision of different ideas and skills leads to artistic movements and technological breakthroughs. The connections themselves become a generative force. In the cosmos, the gravitational network facilitates colossal collisions and mergers between galaxies. These violent events are not just destruction. They are also triggers for intense bursts of new star formation, literally forging new solar systems and seeding the universe with heavier elements. The network, through its connections, creates the conditions for constant renewal and complexification. This principle ultimately reveals a universe that builds itself through relationship. An atom alone is just an atom, but connect atoms through chemical bonds, and you get molecules with entirely new properties. Connect molecules and you get cells. Connect cells and you get conscious life. Connect stars through gravity and you get galaxies. Connect galaxies and you get a cosmic web. At every scale, reality is woven from a tapestry of connections. The components matter, but it is the relationships between them, the gravitational pulls, the chemical bonds, the exchanges of information, that truly define the system and unlock its potential. The universe is not a collection of solitary objects. It is a vibrant, dynamic, and infinitely connected network. And it is in the endless dance between its nodes that the great masterpiece of existence is continuously composed. Now, we venture into one of the most mysterious and mind-bending frontiers of self-organization, a principle that seems to blur the very line between the tiny quantum world and our everyday reality. We've been taught that the bizarre rules of quantum mechanics, with their spooky connections and fuzzy probabilities, are confined to the realm of the ultra-small, the world of atoms and particles. But what if these quantum effects aren't confined at all? What if they play a direct and vital role in orchestrating the order we see in the world around us, from the green leaves on a tree to the flight of a bird across a continent? This is the astonishing idea of quantum coherence, a phenomenon where particles stop acting as individuals and begin to move in perfect, coordinated unison, creating states of matter and processes that simply shouldn't be possible under the classical laws of physics. To grasp this, imagine a vast crowd in a stadium doing the wave. For it to work, everyone has to stand up and sit down at precisely the right moment, perfectly synchronized with their neighbors. That's coherence, a collective, rhythmic order emerging from individual action. In the quantum world, this isn't just a metaphor. Take a superconductor, for example. When certain materials are cooled to extremely low temperatures, their electrons overcome their natural repulsion for one another. They form what are called Cooper pairs, and suddenly, all these pairs begin to move in a single, coherent quantum state. This collective behavior means that electrical current can flow through the material forever without any resistance or loss of energy. It's a macroscopic object, a piece of metal you can hold in your hand exhibiting a purely quantum mechanical property on a large scale. Similarly, in a Bose-Einstein condensate, a cloud of atoms is cooled to near absolute zero. At that point, the atoms lose their individual identities and merge into a single, giant superatom, all described by the same wave function. They behave as one entity, a dramatic and visible manifestation of quantum weirdness at a scale we can actually see. For a long time, physicists assumed these were exotic laboratory curiosities, that the warm, wet, and noisy conditions of the everyday world would instantly destroy any fragile quantum coherence. But nature, it seems, has found a way. Consider the incredible efficiency of photosynthesis, the process that powers nearly all life on Earth. When a photon of sunlight strikes a leaf, its energy is absorbed by a molecule in a chloroplast. Classically, we'd expect that energy to then bounce around randomly through the forest of molecules like a pinball, until it happens to find the reaction center where it's used to make sugar. This would be a slow and wasteful process, but that's not what happens. Experiments have shown that the energy doesn't take a single path. Thanks to quantum coherence, it effectively explores all possible pathways through the molecular network simultaneously in a wave-like manner, instantly and efficiently finding the most optimal route to its destination. It's a quantum-assisted search algorithm operating at room temperature inside a living plant, making the process nearly 100% efficient. The green world around us is literally harnessing quantum mechanics to feed the planet. Perhaps even more astonishing is the case of bird navigation. Species like the European robin migrate thousands of miles with pinpoint accuracy. How do they do it? They are thought to use a compass sense based on Earth's faint magnetic field. But the problem is, that field is incredibly weak, far too weak to directly influence a chemical reaction in the classical way. The leading theory points to quantum coherence again. In the robin's eye, a protein called cryptochrome is thought to host a pair of electrons. When a photon of light hits this protein, it creates a pair of electrons that are quantum entangled, their fates linked in a way that Einstein famously called spooky action at a distance. The subtle influence of Earth's magnetic field affects the quantum spin state of these entangled electrons, which in turn alters the chemistry of the protein, sending a signal to the bird's brain that tells it which way is north. This would mean a bird's brain is essentially performing a quantum measurement, using the spookiest phenomenon in physics as a practical tool for survival. It suggests that evolution has been leveraging quantum mechanics for millions of years. This radical idea that quantum processes can persist and be functional in the macroscopic, biological world forces us to reconsider the relationship between the quantum and classical realms. They may not be separate worlds at all, but exist on a seamless continuum. This perspective is pushed to its ultimate extreme in some of the most ambitious theories of modern physics. The holographic principle, for instance, suggests that all the information describing our three-dimensional universe, including everything within it, might actually be encoded on a two-dimensional surface at its boundary, much like a hologram where a 3D image emerges from a flat sheet. In this view, the universe itself might be a kind of macroscopic quantum system, a projection of entangled quantum information. Theories of quantum gravity, which seek to unify general relativity with quantum mechanics, also propose that the fabric of spacetime itself might emerge from a more fundamental network of quantum relationships. The smooth, continuous space we experience could be the classical, large-scale outcome of countless tiny, discrete quantum events happening at the Planck scale. The order of the cosmos, from the rotation of galaxies to the force of gravity, might literally be built from the ground up by quantum coherence and information processing. A powerful metaphor for all of this is the common laser. In an ordinary light bulb, atoms release photons randomly, in all different directions and phases. The result is incoherent light, a diffuse, warm glow. But in a laser, the atoms are stimulated to emit photons that are all perfectly in sync. Same wavelength, same direction, same phase. This is coherent light. The photons cease to act as individuals and become a unified, powerful beam capable of precise, focused work, from reading a DVD to performing surgery. In a very similar way, we can imagine the universe using the principle of quantum coherence to transform a chaotic, primordial soup of particles into the focused, ordered, and complex reality we inhabit today. It's as if the cosmos found a way to create a laser-like beam of existence from the initial incoherent flash of the Big Bang. This principle challenges us to see everything, from the formation of a star to the firing of a neuron, not as purely classical events, but as phenomena deeply rooted in the synchronized, interconnected, and fundamentally quantum underpinnings of reality. The universe builds itself by getting its smallest pieces to act in concert, and in that harmony, the macroscopic world is born. But if the universe is indeed a vast, interconnected network built upon quantum foundations, then how did it arrive at such a precise and life-friendly set of rules in the first place? This question leads us to a principle that beautifully merges the ideas of chance and necessity, suggesting that the cosmos itself might be subject to a form of natural selection. We often think of evolution as a biological process, the mechanism that sculpted the diversity of life on Earth through random mutation and environmental filtration. But what if this same basic logic of trial, error, and selection operates on a far grander scale, shaping the very laws of physics and the architecture of reality? This is the profound concept of adaptive evolution applied to the cosmos, a form of self-organization where the universe isn't just building structures within itself, but might actually be tuning its own fundamental parameters through a process of cosmic selection. At the heart of this idea is a simple but powerful observation. Our universe appears to be incredibly fine-tuned for complexity and life. Physicists have identified a number of fundamental constants, like the strength of gravity, the mass of an electron, or the force that binds atomic nuclei, that seem perfectly calibrated. If any one of these values were even slightly different, the consequences would be catastrophic. A slightly stronger gravitational constant, and the universe would have collapsed back on itself immediately after the Big Bang. A slightly weaker force holding atoms together, and no elements heavier than hydrogen could ever form. There would be no planets, no chemistry, and certainly no observers to wonder about it all. This incredible precision is known as the fine-tuning problem, and it begs for an explanation. It feels as though the cosmos has been carefully engineered, but by whom or what? One compelling answer is that it engineered itself through a process of selection. This is where the anthropic principle enters the stage. In its simplest form, the anthropic principle states that we can only observe a universe that is capable of producing us. It's a selection effect. If the constants of nature weren't just right, we wouldn't be here to notice. But this observation alone feels like a tautology. It doesn't explain why such a lucky universe exists. To move beyond this, some scientists like Lee Smolin and others have proposed theories where the fine-tuning isn't a one-off miracle, but the result of an evolutionary process. Imagine a multiverse, a vast and perhaps infinite ensemble of universes, each with its own randomly selected set of physical laws and constants. In most of these universes, the numbers are all wrong. They might collapse instantly, or expand into a thin, featureless void, or never form atoms. These are cosmic stillbirths, universes that fail to generate any complexity. But among this unimaginably vast number of failed experiments, a tiny fraction, by pure chance, get the numbers just right. These rare universes become stable, long-lived, and fertile. They can form galaxies, stars, planets, and ultimately life. We, of course, find ourselves in one of these successful universes, not because it was designed for us, but because we are a product of its success. We can see a powerful analogy for this in the story of stellar nucleosynthesis, the process by which stars forge the elements of the periodic table. The first stars were born from pure hydrogen and helium, the simple remnants of the Big Bang. Within their fiery cores, these stars acted as immense nuclear furnaces, running a trial-and-error process of fusion. They tried to fuse protons and neutrons into heavier elements, and most of these reactions were dead ends, producing unstable isotopes that quickly fell apart. But through countless failed attempts across billions of stars, a few pathways proved stable and successful. They found ways to forge carbon, oxygen, iron, the very building blocks of planets and life. These stable elements were then scattered across the cosmos in supernova explosions, seeding future generations of stars and solar systems with the successful results of this stellar evolution. The universe wasn't built with these elements from the start. It had to evolve them through a process of nuclear selection, where stable patterns endured and unstable ones vanished. In a similar way, the laws of physics themselves might be the stable, enduring results of a much deeper cosmic evolution. This perspective completely reframes our understanding of cosmic history. It invites us to see the timeline of the universe not as a single, predetermined narrative, but as an evolutionary journey, a branching tree of possibilities where successful structures replicate and propagate. A stable star like our Sun isn't just a static object. It's a factory that produces heavier elements, effectively creating the raw material for new planetary systems and potential new life. It's a self-replicating pattern on a cosmic scale. Galaxy collisions, while violent, can trigger bursts of new star formation, effectively spawning new generations of stellar systems. The universe seems to be filled with processes that allow successful configurations to beget more successful configurations, much like a successful biological organism passes on its genes. This suggests that self-organization is the engine of this cosmic innovation, constantly generating new variations, new atomic structures, new stellar systems, new galactic forms, upon which the impersonal forces of physics can act, selecting for stability and longevity. Viewing the cosmos through this evolutionary lens does more than just solve a puzzle about physical constants. It imbues the universe with a sense of history and dynamism. It becomes a learning system, one that explores the space of all possible realities through trial and error, remembering what works and discarding what doesn't. The laws we hold as fundamental and eternal may simply be the local, stable equilibrium that this particular universe has settled into. The winning strategy in a cosmic game of selection that has been playing out for eternity. This is not a universe that was perfectly designed from the top down, but one that built itself from the bottom up, discovering its own rules through a billion failed experiments and a few magnificent successes. It is a vision of reality that is both humbling and empowering, suggesting that the order we see is not a gift from a designer, but a hard-won achievement in an endless struggle for existence, and that we are not merely passive inhabitants, but active participants in this ongoing, evolutionary saga. But if the universe evolves through a process of cosmic selection, refining its own parameters over deep time, what is the fundamental currency of this incredible process? What is the raw material that is being shaped and refined? This brings us to a principle so profound that it reframes our entire conception of reality, suggesting that the bedrock of existence isn't energy or matter, but something even more elemental: information. Information theory provides a breathtaking framework where we can view the entire cosmos not as a collection of things, but as an immense, ongoing computation, a cosmic computer processing the very bits of reality into existence. In this view, the laws of physics are not just equations in a textbook. They are the algorithms running on the hardware of the universe, and everything we see, from a swirling galaxy to a human thought, is the output of this grand informational process. To grasp this, we first need to understand the deep and surprising connection between information and a concept we've already explored: entropy. We discussed entropy as a measure of disorder and a driver of self-organization. But there's a brilliant flip side to this coin. A state of low entropy is actually a state of high information. Think of a beautifully organized library. Every book is in its precise place on a specific shelf, following a meticulous system like the Dewey Decimal System. This highly ordered, low-entropy state contains a vast amount of information because the position of each book tells you something specific. Now imagine a tornado rips through that library. The books are scattered everywhere in a chaotic, high-entropy mess. In this disordered state, the information about where any specific book should be is lost. The organized state has more information than the disordered one. This is the core insight. Information is a form of order, and the universe's drive to create complex, low-entropy structures is fundamentally a process of information processing and storage. We see this principle actively building reality all around us. Consider the molecule of DNA in every one of your cells. It is quite literally a biological hard drive, a molecule that stores digital information in a 4-letter chemical code. This information isn't just a passive blueprint. It's an active program that directs the sophisticated machinery of the cell to build proteins, replicate itself, and ultimately construct and maintain your entire body. Your existence is the physical manifestation of information being read and executed. On a cosmic scale, even a black hole, the ultimate symbol of destruction and entropy, is now thought to be an immense storehouse of information. According to the holographic principle, all the information that describes everything that ever fell into a black hole might be encoded on its 2-dimensional event horizon, the surface that shrouds it from view. The universe seems to be in the business of preserving information, even in its most extreme environments. This leads to a truly radical idea. What if the universe itself is a quantum computer? This isn't just a cute metaphor. Pioneering physicists like John Archibald Wheeler proposed the it-from-bit hypothesis, suggesting that every particle, every force field, and even space-time itself ultimately derives its existence from binary answers to yes or no questions, from bits. In this view, the universe is fundamentally computational at its core. The Big Bang wasn't just an explosion of energy, it was the initialization of a state, the first input into a cosmic processor. The subsequent expansion and cooling represent trillions of years of runtime, where simple initial rules are iterated over and over again to generate the incredible complexity we see. The formation of a galaxy isn't just gravity pulling on gas. It's a gravitational algorithm running its course. The evolution of life is a biological algorithm exploring fitness landscapes. From this perspective, reality is the output of a computation. We can use a simple example from our own technology to illustrate how this might work. Think about data compression, the technology that lets you store a high-definition movie on your phone. Compression algorithms like zip or MPEG work by finding patterns and redundancies in the raw data. They replace long, repetitive strings with much shorter symbols or instructions. The compressed file is a highly ordered, low-entropy state that contains all the information needed to reconstruct the original. In a very similar way, the laws of physics might be nature's ultimate compression algorithm. The entire, seemingly infinite complexity of the cosmos could be generated from a surprisingly small set of fundamental laws and constants. The universe is effectively unpacking itself from a compressed initial state, and we are watching that decompression happen in real time over billions of years. This computational view doesn't diminish the wonder of the cosmos. It deepens our appreciation for its elegant, logical foundation. It suggests that the universe is built not on magic, but on a kind of sublime mathematical reason. The search for a grand unified theory or a theory of quantum gravity is, in essence, the search for the universe's source code. Every time a physicist writes an equation that describes how particles interact or how space curves, they are reverse engineering a small part of this cosmic program. Recognizing this transforms our relationship with reality. We are not just passive beings living in a universe of stuff. We are patterns of information, temporary self-aware expressions of the universe's own computational process, capable of observing itself and slowly, miraculously, beginning to understand the algorithms that gave it birth. This brings us to a principle that might be the most humbling and profound of all. one that challenges our deepest intuitions about what is real and what is not. We are used to thinking of objects as having inherent, fixed properties. A rock is heavy, an electron has a specific spin, a galaxy is a certain size. We imagine these qualities exist within the things themselves, independent of everything else. But what if this is a fundamental illusion? What if the properties of everything in the universe, from the tiniest particle to the largest cluster of galaxies, do not reside within the objects, but instead arise purely from their relationships and the context they find themselves in? This is the revolutionary idea of relationality, a perspective that tells us nothing in the cosmos has meaning or existence in isolation. Everything is defined by its dynamic connections to everything else. We can find stunning evidence for this in both of the great pillars of modern physics. Let's start with Einstein's theory of relativity. Imagine two astronauts, each in their own identical spaceship, moving at a constant velocity relative to each other. If they each measure the length of their own ship and the tick of their own clock, they will get the same answers. The properties seem inherent. But now, if they look at each other's ship, something incredible happens. Each astronaut will measure the other's spaceship as being shorter than their own, and each will see the other's clock ticking more slowly. There is no absolute answer to the question, how long is that ship? Or how fast is that clock ticking? The answers are entirely relative. They depend completely on the relationship between the observer and the observed. Length and duration are not inherent properties of the spaceship. They are properties that emerge from the relative motion between the two frames of reference. There is no privileged, God's-eye view of the universe. Reality is not a static stage. It is a dynamic interplay of perspectives. Now, dive into the quantum world, and the idea of relationality becomes even more pronounced and bizarre. Take a quantum particle like an electron. We might say it has a property called spin. But unlike a spinning top, this spin doesn't have a definite value until we measure it. Before measurement, the electron exists in a fuzzy cloud of potentialities, a superposition of all possible spins. It is only at the moment of measurement, the moment it interacts with a measuring device, that its spin crystallizes into a specific value. And this is where it gets truly strange. In experiments with entangled particles, two particles can become linked so that measuring the spin of one instantly determines the spin of the other, no matter how far apart they are. The property of the second particle isn't determined by anything inherent within it. It is determined solely by its relationship to its partner and the act of measurement. The particle has no standalone reality. Its state is entirely contextual, defined by its relationship within the entangled pair and its interaction with the wider world. This principle scales up dramatically from the quantum to the cosmic. Consider a galaxy. What even is a galaxy? It's not just a collection of stars. It is a gravitational relationship. Its shape, its size, its very existence as a coherent structure is defined by the endless dance of countless stars, all pulling on each other across vast distances. If you could magically remove all but one star, that remaining star would not be a galaxy. The property of being a galaxy is not inherent to any single star. It is a collective property that emerges only from the gravitational relationships between them. Furthermore, a galaxy's identity is shaped by its external relationships. A galaxy in a dense cluster, constantly interacting and even colliding with its neighbors, will have a very different shape, star formation rate, and ultimate fate compared to a lonely, isolated galaxy drifting in a void. Its story is written by its connections. Perhaps the most beautiful and accessible example of this co-creation of reality is the humble rainbow. We point to the sky and say, "Look, there's a rainbow." But where exactly is it? If you move, the rainbow moves with you. Another person standing 50 meters away will see their own rainbow in a slightly different location. The rainbow has no independent existence. It is not an object hanging in the atmosphere. It is a phenomenon that only comes into being through a specific relationship. The precise alignment of the sun behind you, millions of water droplets in the air in front of you, and your own eyes as the observer. The rainbow is a verb, not a noun. It is an event, a process of interaction between light, water, and perception. It is a perfect metaphor for the universe itself, suggesting that what we perceive as solid and separate objects are really temporary patterns in an endless web of relationships. This relational view completely shatters the idea of absolutism, the notion that there is a single, objective reality out there waiting to be discovered. Instead, it presents a universe that is participatory. Reality is not a pre-recorded movie that we are passively watching. It is more like an improv performance where our observations and interactions are part of the script. This doesn't mean we create reality out of nothing with our minds, but it does mean that the specific properties we measure and experience are co-determined by the questions we ask and the interactions we initiate. The universe reveals different aspects of itself depending on how we engage with it. This perspective invites us to see ourselves not as outsiders looking in on a foreign cosmos, but as deeply embedded participants in a reality that is constantly being negotiated and woven together through an infinite number of dynamic connections. A cosmic conversation where everything is defined by its relationship to everything else. But if the universe is a web of relationships, constantly defined by its interactions, then how does it manage to maintain such stunningly complex and stable structures over vast stretches of time? The answer lies in a seeming paradox, a principle that reveals how the cosmos thrives on imbalance. We often picture order as something that exists in calm, stable, and closed systems, a crystal sitting on a shelf, perfectly formed and unchanging. But the most vibrant, creative, and enduring structures in the universe follow a completely different rule. They are what we call dissipative structures, and they perform a kind of magic. They maintain their intricate internal order not by conserving energy, but by constantly dissipating it, by thriving far away from the peaceful stillness of thermodynamic equilibrium. To understand this, we first need to grasp what equilibrium means. Imagine a cup of hot coffee sitting in a cold room. Left alone, the heat energy will flow out of the coffee, warming the air around it until everything reaches the same lukewarm temperature. At that point, the energy has spread out evenly, everything is uniform, and no further net change occurs. This is a state of thermodynamic equilibrium, a state of maximum entropy, where all energy gradients have been flattened and all interesting activity has ceased. It's a state of ultimate rest, but also a state of death for complex systems. Now, contrast that with a living organism like a human being. Your body maintains a constant internal temperature of around 37 degrees Celsius, a highly ordered state that is radically different from your surroundings. You do not drift toward the temperature of the room. You are a pocket of persistent inequality, and you maintain this order through a relentless process. You take in concentrated energy from food, you use it to power your cells, and you continuously dissipate waste heat and molecules back into your environment. You are a whirlpool of organization sustained by a constant flow of energy. If that flow stops, you rapidly decay back toward equilibrium. Your existence is a continuous dance away from balance. This beautiful concept was pioneered by the chemist Ilya Prigogine, who won a Nobel Prize for showing how order can spontaneously emerge in open systems that are flooded with energy. He demonstrated that equilibrium is not the destiny of complex systems, it is their grave. True, vibrant life exists in what he called far from equilibrium conditions, where powerful energy flows keep a system poised on the edge of change, allowing for incredible innovation and self-organization. We can see this in a stunning chemical demonstration called the Belousov-Zhabotinsky reaction. In a dish, you mix a few simple chemicals and then just watch. Instead of simply turning a uniform color as it drifts toward equilibrium, the solution spontaneously erupts into a mesmerizing display of swirling, concentric waves and spirals of color that pulse and dance for minutes on end. This intricate, evolving order is not being imposed from the outside. It is emerging directly from the chemistry itself, powered by the constant flow and dissipation of energy within the mixture. It is a simple, beautiful analog for how complexity can bloom from imbalance, and we see this principle etched across every scale of reality. A hurricane is a terrifyingly powerful dissipative structure. It is a masterpiece of organized chaos, a vast engine that forms over warm ocean water. It maintains its iconic spiral structure and furious winds by drawing in warm, moist air from the ocean surface. This air rises, releasing its latent heat as it condenses into clouds and rain. This released energy is the fuel. The storm then dissipates this energy through its powerful winds and rain, eventually losing its power when it moves over land or cold water, cutting off its energy supply. It is not a static thing. It is a process, a temporary pattern sustained by a continuous flow of energy from the sun, ultimately radiating that energy back into the upper atmosphere. Its entire existence is a fight against equilibrium, a fight it is destined to lose but which creates its breathtaking, fearsome order in the meantime. Even the gentle flame of a candle is a dissipative structure. It seems so simple, but it's a brilliant example of self-organized complexity. The flame has a distinct, teardrop shape that it maintains consistently. It doesn't just explode or flicker out randomly. This stable form exists because the candle is continuously supplying it with fuel, the liquid wax drawn up the wick. The flame then burns this wax, combining it with oxygen from the air in a chemical reaction that releases light and heat. The shape of the flame is precisely determined by the balance between the inflow of fuel and the outflow of heat and reaction products. It is a dynamic structure, constantly consuming and constantly dissipating, and the moment you snuff out the flow of either fuel or oxygen, the pattern instantly collapses. It is a miniature star, persisting through constant exchange. This principle scales all the way up to the grandest cosmic structures. A star, like our Sun, is the ultimate dissipative structure. It is not a static ball of fire. It is a dynamic, stable, and long-lived nuclear furnace that maintains its intricate internal balance for billions of years. How it constantly pulls in the gravitational energy of its own immense mass, creating the pressure and heat at its core to fuse hydrogen into helium. This fusion releases a colossal amount of energy in the form of light and heat, which radiates out into the cold vacuum of space. The star is in a perfect, steady-state dance. The inward crush of gravity is balanced by the outward push of radiation pressure from the energy being generated and dissipated. It is this magnificent, constant flow of energy, from gravitational potential to nuclear fusion to radiated starlight, that allows the star to persist in its complex, ordered state, far from the dull equilibrium of a cold, dark cloud of gas. It is a candle on a cosmic scale, and its sustained burning is what provides the energy and the heavier elements that make planets and life possible. The universe builds itself not in the quiet of balance, but in the roaring, dynamic, and creative flow of energy, forever moving and forever becoming. Now, having explored how the universe thrives on dynamic flows and relational existence, we turn our attention to the very stage upon which this grand drama unfolds, the shape of space itself. This brings us to the fascinating world of topology, a branch of mathematics that is less concerned with precise distances and angles and more with the most fundamental, unchanging properties of shapes. Imagine a donut and a coffee cup. To a topologist, these are essentially the same object because each has exactly one hole. You can theoretically mold a soft clay donut into a coffee cup without ever breaking the clay to create a new hole or seal one up. Topology is the study of these persistent features, the properties that remain invariant no matter how much you stretch, twist, or bend an object. It asks the deep questions: what is the fundamental shape of our universe? How is it connected? And how do these global, geometric properties dictate the physical laws that operate within it, guiding the cosmos in its relentless self-construction? This abstract mathematical concept has profound and very real consequences for the physics of our universe, right down to the devices you might be using right now. In the field of condensed matter physics, scientists have discovered states of matter where the electronic properties are protected by their topology. These are called topological insulators, materials that are electrical insulators on their interior but conduct electricity perfectly on their surface. What's incredible is that this conducting surface state is incredibly robust. You can scratch the material, introduce impurities, or deform it slightly, and the conduction persists. This is because the property is not dependent on the perfect arrangement of atoms, but on the overall topological invariant of the material's electronic structure, a kind of mathematical knot that cannot be easily undone. This robustness, born from geometry, is a powerful form of self-organization, allowing for stable, error-resistant states that are crucial for the next generation of quantum computing and electronics, showing how the universe can build resilient systems based on abstract mathematical principles. The influence of topology extends far beyond the lab, all the way to the largest possible scales. Cosmologists have long debated the overall shape, or topology, of the universe. Is it finite or infinite? Is it simply connected like a plane, or multiply connected like a torus? One intriguing possibility is that the universe might have a complex folded topology. For instance, if the universe were shaped like a giant donut, a torus, then if you could look far enough in one direction, you might eventually see the back of your own head, as light would wrap all the way around the cosmos. While we haven't observed such ghostly duplicates, the overall topology of the universe has a direct impact on what we can see. It influences how light from the cosmic microwave background propagates and patterns itself, leaving subtle imprints that experiments are desperately searching for. The very connectivity of space dictates the pathways of information and energy, setting the foundational rules for how the cosmic web can form and evolve. We can grasp these mind-bending ideas with simpler, tangible objects. Take a Möbius strip, a ribbon with a single half-twist before its ends are joined. This simple act creates a surface with only one side and one edge, a property that is purely topological. Run your finger along the surface, and you'll traverse both sides without ever crossing an edge. This strange connectivity isn't just a mathematical curiosity. It's a model for how the universe might be wired together in non-obvious ways. Similarly, the field of knot theory studies the different ways a loop can be tangled in 3 dimensions. A knot isn't defined by how tight or loose it is, but by the essential way the string is intertwined, a topological invariant. Nature uses this principle in the incredibly long molecules of life. DNA within your cells becomes highly knotted during replication, and special enzymes act as topological surgeons, cutting and rejoining the strands to resolve these knots and ensure the genetic code is read correctly. This is self-organization at the molecular level, governed by geometry. All of this rests upon the revolutionary insight from Einstein's general relativity, that space is not a static, empty stage. Instead, the stage itself is dynamic and malleable. Mass and energy tell spacetime how to curve, and that curved geometry, in turn, tells mass and energy how to move. The planets orbit the Sun not because of some mysterious force pulling them, but because they are following the straightest possible paths, geodesics, through a spacetime valley curved by the Sun's mass. This is the geometric framework for cosmic evolution. The topology of the universe provides the global rules of connectivity. Is space open, closed, or flat? Is it simply or multiply connected? While the local curvature sculpted by galaxies and dark matter dictates the local dynamics, guiding the flow of gas, the birth of stars, and the rotation of galaxies. The universe builds its structures not in a featureless void, but upon a flexible, geometric fabric where shape and connectivity are the ultimate architects, dictating function and form at every scale. Now consider the silent, celestial dance happening right above our heads. The planets in our solar system don't just orbit the sun in isolation. They fall into gravitational rhythms with one another, a cosmic phenomenon known as orbital resonance. Take Neptune and Pluto, for instance. For every 2 complete orbits that Neptune makes around the Sun, Pluto makes exactly 3. This isn't a mere coincidence. It's a stable, synchronized pattern locked in by gravity. These resonances create gravitational sweet spots, like the Lagrange points, where objects can reside in harmonious balance with larger bodies. This same principle of synchronization acts as a fundamental organizing force throughout the cosmos, preventing chaotic collisions and ensuring the long-term stability of solar systems, allowing for the calm, predictable environments necessary for planets like Earth to exist and thrive for billions of years. This incredible capacity for spontaneous synchronization isn't limited to the grand scales of astronomy. We can witness it in our own backyards on a warm summer evening. In certain parts of the world, thousands of male fireflies will gather in a mangrove tree and, without any central conductor, begin to flash their bioluminescent lights in perfect, sweeping unison. Initially, they flash at random, each insect following its own internal rhythm. But as they see the flashes of their neighbors, they make tiny adjustments to their own timing, slowly and subtly shifting their rhythm to match. This process of mutual adjustment continues until the entire tree pulsates as a single, coherent beacon. There's no leader firefly issuing commands. This stunning visual display emerges entirely from local interactions, a simple rule where each individual responds to the cues immediately around it, resulting in a magnificent global pattern. It's a powerful testament to how complex coordination can arise from the bottom up. Neuroscience reveals that this same process is happening inside each of us right now. Your brain is a vast network of billions of neurons, and their communication is what gives rise to your thoughts, perceptions, and consciousness. This communication doesn't happen through random noise. It occurs through the synchronization of neural firing. When you focus on a task, neurons in specific brain regions begin to fire their electrical impulses in coordinated rhythms, like a crowd chanting in unison. These synchronized brain waves, which we can measure with an EEG, are believed to be crucial for binding together different pieces of information, the sight of a face, the sound of a name, into a single, coherent experience. When this synchronization fails, as it can in certain neurological disorders, perception can become fragmented and disjointed. The very coherence of our reality seems to depend on this internal, biological symphony of timing. To understand the mathematics behind this universal tendency to sync up, scientists turn to elegant models like the Kuramoto model. Imagine a group of metronomes, each ticking at its own natural, slightly different frequency. Now, imagine placing them all on a movable platform that can gently sway. Even though they started out of sync, the tiny vibrations each metronome transfers to the platform will begin to influence all the others. Through this weak coupling, they will gradually entrain one another, their ticks and talks aligning until the entire group is clicking in perfect harmony. The Kuramoto model translates this into a beautiful set of equations that describe this very process, showing how a critical threshold of coupling strength can trigger a phase transition from disorder to global synchrony. It provides a universal mathematical language for sync, applicable from coupled lasers to the beating of pacemaker cells in your heart. This brings us to a powerful metaphor for the cosmos itself, a great orchestra tuning up before a performance. Initially, the hall is filled with a cacophony of sound as each musician independently tests their instrument, each playing their own note at their own tempo. But then, they all turn their attention to the oboe, which sounds a single, pure reference note, and a 440 Hz. One by one, the violinists, the cellists, the brass players, all listen and adjust the tension in their strings, the length of their tubing, subtly shifting their own output to match that fundamental frequency. They are not just matching a pitch. They are aligning their phase, their timing, until the entire orchestra resonates together with a rich, unified tone. In that moment, the individual players become a single, cohesive instrument. This is precisely how the universe coordinates its countless components. The fundamental constants and laws of physics act as that reference tone, and through countless local interactions, whether gravitational, electromagnetic, or quantum, particles, planets, and galaxies all subtly adjust their rhythms, finding a shared harmony in the vast cosmic symphony, creating the coherent, interconnected reality we are part of. Now, consider a truly extraordinary kind of feedback loop, one that doesn't just regulate or amplify a system, but one that has the power to literally bootstrap itself into existence from almost nothing. This is the principle of autocatalysis, a process where the very products of a reaction act as the catalysts that produce more of themselves, creating a self-fueling, exponential engine of creation. Imagine a magical fire that, as it burns, doesn't just consume its fuel but actually manufactures more kindling and more matches, causing the flames to spread faster and faster until they become an unstoppable, self-sustaining inferno. This isn't just a metaphor. It's a powerful chemical reality that may hold the key to how the universe ignites complexity from the most humble of beginnings. We can witness this self-amplifying magic in a beautiful chemical demonstration known as the Formose reaction. Start with a simple, inert mixture of formaldehyde, a basic one-carbon molecule. On its own, it just sits there. But introduce a tiny speck of a mineral catalyst, a simple calcium hydroxide as a spark, and something incredible happens. The reaction begins to produce 2 carbon sugars. Then, some of those 2 carbon molecules spontaneously catalyze the formation of 4 carbon sugars. Those, in turn, help catalyze even more complex molecules, and so on in a rapidly branching, accelerating cascade. Before long, the entire solution is teeming with a diverse, complex soup of sugars, all generated from that single, simple starting ingredient. The system has quite literally built itself up by its own bootstraps, creating its own catalysts and its own complexity in a runaway explosion of organic creativity. It's a stunningly simple laboratory model for how the prebiotic Earth might have crossed the critical threshold from sterile chemistry to the rich, molecular diversity necessary for life to emerge. This concept of an autocatalytic set, a closed, self-sustaining network of reactions where every product is a catalyst for another reaction in the loop, is a leading theory for the origin of life itself, abiogenesis. The famous chicken and egg problem of biology, which came first? The metabolic network that builds proteins or the genetic code that defines them, might be solved by this idea. Instead of a single miraculous molecule like RNA appearing fully formed, the first spark of life may have been a collective phenomenon. A humble, messy web of simple chemical reactions could have accidentally fallen into an autocatalytic cycle. Once that loop closed, the system would have become self-sustaining, capable of drawing in energy and raw materials from its environment to perpetuate and complexify itself. It wouldn't need an external blueprint. Its own internal, recursive logic would be its guide. From that point on, evolution could take over, favoring those autocatalytic sets that were more efficient or more robust, eventually leading to the encapsulation of these processes within cell membranes and the eventual development of genetic information to better stabilize and replicate these successful patterns. Life in this view is not a thing that suddenly switched on, but a self-reinforcing process that ignited and began to burn on its own. And the reach of this principle extends far beyond our planet, all the way to the hearts of stars. The process of stellar nucleosynthesis is a form of cosmic autocatalysis. In the core of a first-generation star, the intense pressure and heat begin to fuse hydrogen atoms into helium, releasing the energy that makes the star shine. This is the initial reaction, but as the star ages and the helium accumulates, it begins to act as a catalyst for its own production in a more complex way. The helium nuclei can then fuse together to form beryllium, and that beryllium can rapidly capture another helium nucleus to form carbon. This is the famous triple alpha process, a key autocatalytic step that unlocks the creation of all heavier elements. The presence of carbon then acts as a catalyst for further fusion processes, leading to oxygen, neon, and all the way up to iron. The star, through its own internal processes, creates the very elements that fuel the next stages of its own nuclear burning. And in its final supernova death throes, it scatters these newly forged elements across space, where they become the raw material for new stars, new planets, and eventually, new life. The star's life cycle is a self-amplifying process that enriches the universe, making future, more complex stars and planetary systems possible. We even see this pattern reflected in the structure of our human economies, which are themselves complex, evolving systems. A simple innovation, like the development of the Internet, creates new platforms for communication. Those platforms then act as a catalyst for further innovation. E-commerce, social media, cloud computing, which in turn creates new markets and new wealth. This new wealth funds more research and development, which catalyzes the next wave of technological breakthroughs. It's a positive feedback loop of economic and technological autocatalysis, where growth begets more growth, and the system becomes increasingly complex and interconnected. Of course, these cycles aren't infinite. They eventually face constraints and require new energy inputs, much like a chemical reaction running out of reactants. But for a time, they exhibit that same signature characteristic of exponential, self-driven expansion. This is the profound power of autocatalysis. It embodies the very essence of self-organization because the system doesn't just respond to its environment. It actively creates the conditions for its own persistence and growth. It becomes autonomous, self-reinforcing, and self-directed. A simple set of rules, once it stumbles into a recursive loop, can generate its own momentum, creating pockets of order that are remarkably resilient and capable of evolving toward greater complexity. The universe seems to have a deep fondness for these self-starting engines. They are the creative sparks that can take a tiny fluctuation, a random chance encounter between molecules, or a slight density variation in the early cosmos, and amplify it into a galaxy, a cell, or a civilization. Autocatalysis is the universe's way of whispering a simple secret to itself. A secret that, once heard, echoes and amplifies until it becomes a roar of existence. Yet just as autocatalytic processes show how systems can bootstrap themselves into complexity, the universe reveals another layer of its ingenuity, one where reality itself seems to wear two different masks at once, each telling a different but equally true story about its nature. This is the profound principle of duality, a concept that challenges our everyday intuition by presenting us with two seemingly contradictory descriptions of the same phenomenon, both of which are simultaneously valid and necessary for a complete understanding. It's as if the cosmos is a master storyteller, weaving its narrative through two different languages, and to truly appreciate the plot, we must become fluent in both. The most famous and mind-bending example of this is found in the quantum realm with wave-particle duality. For centuries, physicists argued whether light was composed of particles, as Newton believed, or if it was a wave, as Huygens proposed. The truth, as quantum mechanics revealed, is that it is both, and neither, depending on how you choose to look at it. In the classic double-slit experiment, a single photon of light fired at a barrier with two narrow openings will do something miraculous. If you don't try to measure which slit it goes through, the photon behaves like a wave. It passes through both slits at once, creating an interference pattern of bright and dark bands on a screen behind the barrier, a pattern that can only be explained by waves overlapping and interacting with themselves. But if you place a detector at one slit to catch it in the act, the photon suddenly behaves like a discrete particle, going through one slit or the other and leaving no interference pattern. The very act of observation, the question we ask, forces the photon to choose a face to show us. It's not that light is sometimes a wave and sometimes a particle. It is something more fundamental that presents these two complementary aspects to our instruments. This duality isn't a flaw in our understanding. It is the very nature of reality at its smallest scales, a deep truth that tells us the universe is far richer and more complex than any single perspective can capture. This beautiful interplay of complementary perspectives isn't confined to the weird world of quantum physics. It's a powerful tool we use every day, often without realizing it. Think about sound. When you listen to a symphony, you experience it as a complex, evolving signal in time, the crash of a cymbal here, the sustained note of a violin there. This is the time domain perspective. But that same beautiful sound can be completely translated into a frequency domain perspective using a mathematical tool called a Fourier transform. This process decomposes the entire symphony into its constituent pure tones, each with a precise amplitude and frequency. It tells you exactly how much of a 260 Hz C note is present versus a 440 Hz A note. To a musician, the time domain view is intuitive. To an audio engineer trying to remove a specific hum from a recording, the frequency domain view is indispensable. They are two completely different descriptions of the exact same reality. One is not more real than the other. They are dual perspectives, each revealing truths that are hidden in the other. The time view shows you the melody. The frequency view shows you the harmony. You need both to fully appreciate the music. Perhaps the most ambitious and profound duality in all of theoretical physics is the holographic principle, specifically the AD-S/CFT correspondence proposed by Juan Maldacena. This is a concept so revolutionary it feels like science fiction. In its simplest terms, it proposes a perfect duality between a universe with gravity and a universe without it. On one side of this correspondence is a hypothetical universe known as anti-de Sitter space, which has a specific type of curvature and contains gravity. The physics within this volume of space is described by string theory. On the other side is a quantum field theory that lives on the lower dimensional boundary that encloses that volume. This boundary theory has no gravity in it at all. It's described by particles and forces interacting on a flat surface. The breathtaking claim is that these two descriptions, the gravitational physics in the bulk of the universe and the non-gravitational physics on its boundary, are completely equivalent. They are two different languages describing the exact same underlying reality. Information is not lost, it is preserved perfectly, just encoded in two vastly different ways. It suggests that our familiar three-dimensional world of gravity and stars might be a projection of information stored on a distant, two-dimensional surface, much like a three-dimensional hologram emerges from a two-dimensional film. This isn't just a mathematical curiosity. It provides a powerful way to tackle problems in quantum gravity by translating them into problems in the better understood quantum field theory, and vice versa. It shows us that the universe might build its complexity through a kind of cosmic redundancy, writing the same story in two completely different scripts. A simple and powerful analogy for all of this is a coin. A coin has two distinct sides, heads and tails. If you only ever look at one side, you have an incomplete picture of the object. You might even develop a theory about coins based solely on heads, completely missing the reality of tails. But both sides are essential to its identity. They are different, complementary aspects of the same whole. You can't see both sides at the exact same moment from a single vantage point, but you can flip it over and appreciate the other view, understanding that the coin's true nature encompasses both. In the same way, the universe presents us with dual descriptions. Is light a particle or a wave? The answer is yes. Is a sound a waveform in time or a spectrum of frequencies? The answer is yes. Is reality a volume with gravity or information on a boundary? The answer appears to be yes. This principle of duality teaches us a deep lesson about the architecture of reality. Complexity and depth are often built from interconnected, complementary perspectives that seem contradictory on the surface, but reveal a deeper, more unified truth when embraced together. The universe doesn't limit itself to a single narrative. It speaks in harmonies, and to hear the full symphony, we must learn to listen with more than one ear. Now let's explore one of the most elegant and efficient strategies the universe employs in its construction project, a principle that allows it to build infinite complexity from startlingly simple rules through a process of self-reference. This is the magic of recursion, the extraordinary phenomenon where a system applies a rule or process to itself, creating patterns that nest within themselves like a set of Russian dolls, revealing deeper layers of similarity at every scale. Imagine a story that begins with a character who sits down to read a book. And as you turn the page, you discover the character in the book is also reading a book. And within that book, another character is reading, and so on, diving infinitely inward. This isn't just a clever literary device. It's a fundamental architectural pattern woven into the very fabric of reality. A signature strategy the cosmos uses to build everything from the branching of your lungs to the large-scale structure of the universe itself. We can witness this recursive artistry throughout the natural world. Take a look at a mighty oak tree. Its overall shape is a large trunk splitting into major branches. Look closer, and you'll see each major branch splits into smaller branches in exactly the same way. Zoom in on a twig, and it too exhibits that same branching pattern. Even the veins within a single leaf form a miniature, intricate network that echoes the entire tree's form. This isn't a perfect replica at every level, but the core algorithm, the rule of branch and split, is applied recursively. The tree doesn't need a separate blueprint for every twig and leaf. It simply reuses the same efficient growth protocol over and over again at different scales. This recursive design maximizes the tree's surface area for absorbing sunlight and exchanging gases with minimal genetic instruction. An incredibly economical way to build a complex, living structure. We see this same pattern in the beautiful spiral of a nautilus shell, where each new chamber grown by the creature is a slightly larger copy of the previous one, following a recursive mathematical rule known as the Fibonacci sequence. This incredible power of recursion isn't limited to biology. It's the very engine behind the breathtaking beauty of fractals. A fractal is a geometric shape that is infinitely complex and self-similar, meaning you can zoom in on any tiny part of it and find a pattern that resembles the whole. The branching of a tree, the jagged coastline of a continent, the forking of a lightning bolt, and the intricate structure of a snowflake are all natural fractals. They are generated by recursive processes where a simple formula is iterated repeatedly. The famous Mandelbrot set, that infinitely complex thumbprint of God image, is generated by a single, simple equation fed back into itself trillions of times. From this recursive feedback emerges an endless frontier of intricate and beautiful patterns, a universe of complexity hidden within a simple rule, the artist M. C. Escher masterfully captured this mind-bending quality in his drawings, like drawing hands, where two hands emerge from a flat page to draw each other into existence, a perfect visual metaphor for a recursive loop where the creator and the created are one and the same. In the realm of computer science, recursion is a fundamental tool for solving complex problems with elegant efficiency. A recursive function is one that calls itself within its own definition. Imagine you want to calculate the factorial of a number. Let's say 5 factorial, which is 5 times 4 times 3 times 2 times 1. A recursive function to solve this would say, the factorial of n is equal to n multiplied by the factorial of n minus 1. The function calls itself with a slightly simpler version of the problem, and that new call does the same thing, drilling down until it reaches a simplest case, the factorial of 1, which is defined as 1. Then, all the solutions cascade back up, each function returning its answer to the one that called it, until the original problem is solved. This divide and conquer strategy breaks a massive problem into smaller, self-similar pieces, solving them all with the same concise algorithm. It's a powerful way to navigate complex structures like branching trees of data or intricate networks, mirroring the universe's own method of building complexity through nested, self-referential processes. This principle scales up to truly cosmic proportions. The theory of cosmic inflation suggests that the entire universe underwent a period of exponential, recursive expansion in its first fleeting moments. In this model, a tiny patch of space-time expanded at an incredible rate, and within that expanding space, quantum fluctuations were themselves stretched and amplified, creating new regions that also underwent inflationary expansion. This process could potentially be recursive, with pocket universes budding off within a greater multiverse, each with its own physical constants, all generated by the same underlying inflationary mechanism applying itself over and over. Even the distribution of matter in the cosmos appears recursive. The cosmic web, with its vast filaments and clusters of galaxies, isn't smooth. If you zoom in on a single filament, you'll find it has its own substructure, smaller clusters and knots of galaxies. Zoom in further on a cluster, and you find individual galaxies. This self-similar, hierarchical clustering suggests that the gravitational collapse that formed the largest structures in the universe may have followed a recursive pattern, with clumps forming within larger clumps across many scales. Perhaps the most profound example of biological recursion is the molecule of DNA. The very process of life is maintained through a recursive loop. The DNA in your cells contains the instructions to build proteins, and some of those proteins are enzymes that are essential for the process of replication, the very process that copies the DNA itself. The system is self-referential. DNA codes for the machinery that copies DNA. This beautiful closed loop is the reason life can perpetuate itself. It's a recursive algorithm written in the language of chemistry, allowing a finite set of instructions to build and maintain an organism of immense complexity through countless cycles of cell division and growth. This efficient reuse of information is the hallmark of recursion, allowing for incredible complexity to emerge from a surprisingly simple, though elegant base code. This points to the ultimate power of this principle: scalability and efficiency. Recursion allows the universe to build complexity with a remarkable economy of resources. It doesn't need a unique rule for every scale of reality. A single, well-designed recursive rule can generate a near-infinite array of complex structures, from the microscopic to the galactic. It's a deeply efficient way to encode information. Instead of storing a blueprint for every single branch on a tree, the genome only needs to encode the simple recursive instruction for branching, and then let the process run. This efficiency is why recursive patterns are so ubiquitous. They are nature's favorite way to build robust, scalable, and adaptable systems. The universe appears to be fundamentally recursive in its architecture, with processes and patterns echoing across levels to create a coherent, deeply connected whole. Recognizing this allows us to see the cosmos not as a collection of separate parts, but as a self-referential, elegantly designed system where the same simple melodies are played on different instruments and at different tempos, creating the magnificent and harmonious symphony of existence. But after exploring how recursion allows the universe to build complexity through self-similar patterns, we must now turn our attention to the profound relationships that form between these patterns, revealing a cosmos built not just on solitary structures but on deep, cooperative partnerships. This brings us to the beautiful principle of symbiosis, a form of interaction where two or more different entities come together in a long-term relationship that provides mutual benefit, enhancing the stability, complexity, and resilience of the entire system. We often default to a narrative of competition when we look at nature, the survival of the fittest, the relentless struggle for resources. And while that is certainly a powerful force, it's only half the story. The universe is just as much a master of collaboration, weaving together disparate elements into partnerships that are far greater than the sum of their parts, creating new levels of order and capability that would be utterly impossible for any of the players alone. We can find the most intimate and powerful example of this symbiotic collaboration not in some distant galaxy, but inside nearly every one of your own cells. Billions of years ago, a pivotal event occurred that would forever change the course of life on Earth. A single-celled organism engulfed another, a bacterium capable of a remarkable new trick, using oxygen to efficiently produce energy. But instead of being digested, this bacterium was welcomed. It took up permanent residence, and over eons, it evolved into what we now call the mitochondrion, the powerhouse of the cell. This was not a hostile takeover. It was the beginning of a grand partnership. The host cell provided protection and nutrients, and the mitochondrion provided a torrent of usable energy. This symbiotic alliance, known as endosymbiosis, was so successful that it became the foundation for all complex life, from fungi to plants to animals. Your ability to read this, to think, to move, is powered by the descendants of that ancient bacterial guest. Your body is not a single entity but a vast, cooperative collective of once independent organisms now working in harmonious synchrony, a testament to the universe's power to build through collaboration. This same cooperative logic scales up to shape entire ecosystems. Consider a coral reef, one of the most diverse and vibrant structures on the planet. It is a magnificent underwater city, built from a symbiotic partnership between the coral animal and microscopic algae called zooxanthellae that live within its tissues. The coral provides a safe home and access to sunlight for the algae. In return, the algae, through photosynthesis, produce sugars and other nutrients that feed the coral, fueling its growth and enabling it to build its massive limestone skeleton. This partnership is the engine of the entire reef ecosystem, creating a complex habitat that supports thousands of other species. The reef itself is an emergent property of this symbiosis. It wouldn't exist without this intimate cooperation. When ocean temperatures rise and stress this relationship, causing the coral to expel its algal partners in a process called bleaching, the entire structure and the community it supports are threatened. The health of the whole is dependent on the health of the relationship, and this principle of cosmic collaboration extends far beyond our planet, all the way to the largest structures in the universe. For decades, astronomers were puzzled by how galaxies held themselves together. The visible stars and gas in a spiral galaxy like our Milky Way are rotating so fast that the gravity from all that visible matter shouldn't be nearly strong enough to prevent them from simply flying off into the void. Something invisible had to be providing the extra gravitational glue. That something is dark matter, a mysterious substance that does not emit or absorb light, but whose gravitational influence is undeniable. This is not a story of dark matter acting alone. It's a story of a cosmic symbiosis between dark matter and ordinary, baryonic matter, the stuff of stars, planets, and us. In the early universe, dark matter formed vast, diffuse halos, gravitational wells that acted as seeding ground and scaffolding. Ordinary matter, attracted by this gravity, flowed into these halos, clumping together to form the first stars and galaxies. But then, the ordinary matter gave something back. As stars formed and went supernova, they released powerful winds and radiation that actually helped shape and mold the distribution of the dark matter itself. They work together. The dark matter provides the gravitational framework, and the ordinary matter provides the complex physics that fills that framework with light and structure. They are locked in a cooperative dance, each essential for building the magnificent galaxies we see today. This shift in perspective, from pure competition to include collaboration, reveals a universe that is far more innovative and efficient. Symbiotic relationships are masterclasses in reducing conflict and waste. Instead of two entities fighting over the same scarce resource, they evolve to use each other's waste products or provide complementary services. In your gut, trillions of bacteria help you digest food and train your immune system, while you provide them with a warm, stable environment and a constant supply of nutrients. It's a perfect recycling system. This cooperative efficiency fosters incredible resilience. A system built on multiple, interdependent partnerships is far more robust than a fragile hierarchy. If one partner is weakened, the others can often provide support, allowing the whole system to weather storms and persist through change. This resilience is the hallmark of mature ecosystems, healthy economies, and enduring social structures. Think of a championship sports team. A team filled with nothing of the most talented, ball-hogging superstars, each playing for their own glory, will often lose to a less flashy but more cohesive team where the players understand their roles, trust each other, and pass the ball to whoever is in the best position to score. The team's success is an emergent property of their cooperation. It cannot be found in the skill set of any single player. The whole becomes greater than the sum of its parts. This is the powerful metaphor for our symbiotic universe. The cosmic components, particles, forces, dark matter, galaxies, and even life forms, are not just competing for dominance. They are passing the ball, setting screens, and working together to build a reality that is more complex, more stable, and more beautiful than any of them could ever achieve alone. It reveals a cosmos where collaboration is not a secondary strategy, but a primary, foundational force in the great architectural project of existence. Yet as the universe builds itself through these astonishingly creative and collaborative processes, from the recursive patterns of fractals to the symbiotic dance of galaxies, a profound question emerges. How does it manage to maintain any stability at all amidst this constant flux? How can a cosmos that is forever changing, evolving, and self-organizing provide the consistent, reliable environment necessary for planets to form, for life to emerge, and for consciousness to contemplate it all? The answer lies in a principle of profound constancy, a set of unwavering rules that act as the universe's ultimate anchor, the principle of invariance and the conservation laws that arise from it. These are the non-negotiable, unchanging truths that provide the stable foundation upon which all of the cosmos's dynamic creativity is free to play. At its heart, invariance simply means that certain properties remain constant, no matter what transformations or changes a system undergoes. Think of it as the universe's most sacred vows, promises it never breaks. The most familiar of these are the great conservation laws. The conservation of energy, which states that energy can neither be created nor destroyed, only transformed. The conservation of momentum, which ensures that the total momentum in a system remains constant unless acted upon by an outside force, and the conservation of electric charge, which guarantees that the net charge of an isolated system never changes. These are not mere suggestions or trends. They are ironclad rules that every single particle and force in the cosmos must obey, from the smallest quantum fluctuation to the collision of entire galaxies. They are the unwavering pillars that hold reality together, providing a framework of predictability that allows complexity to safely emerge. We can see the guiding hand of these invariant laws everywhere we look in the cosmic architecture. Consider the elegant, predictable orbit of Earth around our Sun. Why does it trace that same elliptical path year after year, millennium after millennium? It is constrained and shaped by the conservation of angular momentum. As the primordial solar nebula collapsed to form our solar system, any slight rotation it had became amplified, much like a figure skater pulling in their arms to spin faster. This rotational momentum had to be conserved. It couldn't just disappear. So, as the cloud collapsed, it flattened into a spinning disk, and the material within it coalesced into planets that inherited that momentum, locking them into stable, enduring orbits. Without this invariant law, planets would either spiral into their star or be flung off into the void. Solar systems, as stable homes for life, simply could not exist. The conservation of energy plays an equally crucial role in dictating the life story of every star in the sky. A star is a magnificent balancing act between two titanic forces, the inward crush of gravity and the outward push of radiation pressure from nuclear fusion. The star's stability over billions of years is a direct consequence of energy conservation. The gravitational potential energy released as the star contracts is precisely converted into the thermal energy that heats its core to the millions of degrees required for fusion. Then, the energy released by fusion fights back against gravity, maintaining a perfect, steady-state equilibrium. This dance continues until the star exhausts its nuclear fuel. At that point, energy conservation dictates the star's fate. With no new energy being created to oppose it, gravity wins, leading to a dramatic collapse that may result in a supernova explosion, a neutron star, or a black hole. The entire stellar life cycle, from brilliant main sequence star to stellar remnant, is a story written by the unyielding conservation of energy. The deep, beautiful reason why these conservation laws exist was uncovered by the brilliant mathematician Emmy Noether in 1918. Her groundbreaking theorem, now a cornerstone of theoretical physics, revealed a stunning and profound connection between symmetry and invariance. Noether proved that for every continuous symmetry in the laws of physics, there must be a corresponding conservation law. What does this mean? A symmetry in this context means that the laws of physics remain unchanged under a certain transformation. For example, the fact that the law of gravity works the same today as it did a billion years ago is a symmetry in time. The laws are invariant over time. Noether's theorem shows that this temporal symmetry directly implies the conservation of energy. Similarly, the fact that the laws of physics are the everywhere, that an experiment in a lab on Earth gives the same result as in a distant galaxy, is a symmetry of space, and this implies the conservation of momentum. The fact that the laws are the same no matter which direction you face is rotational symmetry, and this gives us the conservation of angular momentum. This is one of the most elegant and powerful ideas in all of science. The unwavering constancy of the universe's rules, their symmetry, is what gives rise to the stable, conserved quantities that make complex reality possible. This bedrock of invariance is what makes the universe a place of trust and predictability. It allows for a cosmos that is both dynamic and dependable. Because energy is always conserved, engineers can design power grids and spacecraft with confidence. Because charge is always conserved, the intricate chemistry of life can proceed with reliable precision. ensuring that the electrical balance in a cell is maintained. These laws are the ultimate constraints, the riverbanks that guide the flowing river of cosmic evolution. They don't stifle creativity, they make it possible. By ruling out an infinite number of chaotic possibilities, they channel change into productive pathways, allowing for the emergence of galaxies, stars, planets, and life. They ensure that the universe's self-assembly is not a random, lawless scramble, but a coherent, orchestrated process where new structures can build upon the stable foundations of the old. In a universe of constant change, these invariants are the North Star, the fixed points that allow the cosmos to navigate its own incredible journey of becoming, providing the dependable architecture that lets us, and all things, exist within it. Yet even with the universe's profound reliance on stable, unchanging laws, its true creative genius is not revealed in moments of perfect calm, but in its breathtaking response to the unexpected. For all its love of symmetry and conservation, the cosmos is not a static, frozen sculpture. It is a dynamic, living system that actively courts disruption, using shocks and surprises as its most powerful tools for innovation. This brings us to a principle that celebrates the creative power of the shake-up. The notion that the most profound growth often comes not from stability, but from a well-timed disturbance. This is the principle of perturbation and adaptive response, the universe's remarkable ability to not just withstand chaos, but to metabolize it, turning random disruptions into fuel for its own evolution and complexification. We can see this principle at work in the most dramatic events in our planet's history. 66 million years ago, a cataclysmic perturbation arrived from the depths of space, an asteroid roughly 6 miles wide, slamming into what is now the Yucatan Peninsula with the force of billions of atomic bombs. In an instant, this impact created a global winter, shattering ecosystems and wiping out the mighty dinosaurs that had dominated the planet for over 150 million years. From our human perspective, it was a tragedy of unimaginable scale and ending. But from the perspective of cosmic self-organization, it was also a brutal but necessary reset. This massive perturbation cleared the ecological stage, removing the dominant players and creating a world of vacant niches and new opportunities. In the aftermath, small, scrappy, adaptable mammals, once relegated to the shadows, seized their chance. Freed from competition and predation, they diversified explosively, eventually giving rise to every furry, flying, and swimming mammal we know today, including, much later, ourselves. The asteroid impact was a horrific disruption, but it was also the key that unlocked a new chapter of biological complexity, demonstrating that the universe often builds by first breaking. This incredible capacity for adaptation isn't limited to biology. It's woven into the fabric of physical systems at every scale. Our own immune system is a masterclass in this principle. Your body is constantly under perturbation from invading viruses and bacteria. When a new pathogen enters, it's a shock to the system. But your immune system doesn't just have a static, fixed set of defenses. It learns. Specialized cells present the foreign invader to your T cells and B cells, which then undergo a rapid process of mutation and selection to design a custom-made antibody perfectly shaped to neutralize that specific threat. The immune system literally uses the perturbation, the antigen, as a template to forge a new weapon. Furthermore, it then stores a memory of this invader, ensuring that the next time this same perturbation occurs, the response will be faster and stronger. The system doesn't just return to its old state, it evolves. It becomes more robust, more knowledgeable, and more resilient because of the challenge it faced. It adapts, and in adapting, it upgrades itself. This idea of becoming stronger through stress is formalized in the powerful concept of anti-fragility, coined by scholar Nassim Nicholas Taleb. Anti-fragility goes beyond mere resilience or robustness. A resilient system, like a rubber band, can withstand a shock and return to its original shape. An anti-fragile system, however, actually improves and grows stronger when exposed to volatility, randomness, and disorder. Imagine two packages sent through the mail. One is labeled fragile, filled with bubble wrap, and will likely break if shaken. Another contains a collection of seeds. The jostling, bouncing, and perturbations of the mail truck are exactly what those seeds need to crack their shells and prepare them to germinate and grow. The shipping process doesn't damage them, it activates them. They are anti-fragile. We can apply this concept to the cosmos itself. The entire large-scale structure of our universe, the vast cosmic web of galaxies and voids, is thought to have originated from the tiniest of quantum perturbations in the first moments after the Big Bang. Those microscopic fluctuations in the energy field were amplified by the violent exponential expansion of inflation, stretched to astronomical sizes, and became the gravitational seeds for all future structure. The universe didn't smooth out these imperfections, it used them. The initial chaos became the blueprint for all order, a truly anti-fragile beginning where the cosmos built its greatest structures from its earliest stresses. We actively harness this principle in our own engineering and design philosophies. Modern architects designing skyscrapers in earthquake zones don't just try to make their buildings rigid and strong enough to resist tremors. Instead, they often incorporate base isolators, flexible pads or bearings that absorb and dissipate the seismic energy, allowing the building to sway and ride out the quake. They design for perturbation. Even more cleverly, some new materials are designed with microcracks that actually divert and halt the propagation of larger, catastrophic fractures. The material is engineered to fail in a controlled, adaptive way that preserves the whole. This mirrors processes in nature, like forest ecosystems that have evolved with periodic wildfires. Some tree species, like the lodgepole pine, have cones that are sealed shut with a resin that only melts and releases the seeds in the intense heat of a fire. The forest doesn't just recover from the perturbation, it requires it for its own renewal and regeneration. The disruption is not an enemy to be vanquished, but a necessary and integral part of the system's long-term health and life cycle. This shifts our entire perspective on cosmic evolution. It is not a slow, steady, and predictable march toward complexity. It is a story of resilience and transformation, punctuated by crises and opportunities. It is a dance with chaos, where the universe willingly engages with disruption, not as a destructive force, but as a creative partner. Gravitational waves from colliding black holes ripple through space-time, a perturbation that subtly reshapes the fabric of the cosmos. Solar flares from a young star might strip the atmosphere from one planet while delivering the organic building blocks for life to another. The universe is constantly testing itself, poking and prodding its own structures, and in doing so, it discovers new possibilities, new configurations, and new levels of order that could never have emerged in a perfectly quiet and still environment. To understand perturbation is to see that the bumps in the road are not obstacles to the journey. They are the very source of its direction and its destination. But just as the universe reveals its genius through its response to disruption and stress, it also compels us to consider a radically different way of seeing reality altogether. One that challenges our instinct to break things down into their smallest pieces. For centuries, the driving force of science has been reductionism, the immensely powerful approach of understanding a system by taking it apart and studying its individual components. By isolating a single variable in a controlled experiment or identifying the fundamental particle, reductionism has gifted us with the laws of physics and the double helix of DNA. But what if this method, for all its glory, can only ever give us half the picture? What if the most important truths about the universe are not found in the isolated parts, but in the unbreakable connections between them. This brings us to the profound and essential principle of holism, the perspective that systems function as integrated wholes, and that the whole possesses properties and behaviors that are not only unexpected, but are fundamentally impossible to predict or understand by looking at the parts alone. We experience this truth in the most intimate way possible every single moment of our lives through the miracle of consciousness. You could, in theory, become the world's greatest reductionist neuroscientist. You could meticulously map every one of the 86 billion neurons in a human brain. You could chart every synaptic connection in its vast network, understand the electrochemical signal of every neurotransmitter, and catalog the exact structure of every fold in the cerebral cortex. With this mountain of data, you would have a complete parts list for a brain. And yet, nowhere in this immense catalog of components would you find the experience of the color red, the feeling of nostalgia, the taste of chocolate, or the sense of self. Consciousness is not a thing that can be found in any one neuron. It is a holistic property that emerges from the dynamic, integrated activity of the entire system. The whole is not just greater than the sum of its parts. It is something entirely different and new. You cannot understand a symphony by studying each note in isolation. You have to listen to the music they create together. This emergence of holistic properties from local interactions is a universal theme, beautifully illustrated by the field of Gestalt psychology. Gestalt theorists gave us a simple but powerful phrase: the whole is other than the sum of its parts. They demonstrated this with visual illusions like the famous Rubens vase, where the same image can be seen either as a vase or as two faces in profile. Your perception flips between two competing wholes. You cannot see both interpretations simultaneously. Your brain is not passively receiving data. It is actively organizing that data into a cohesive, holistic perception. The faces or the vase are emergent properties of the entire arrangement of lines and shapes. Your mind imposes a unified reality onto the sensory input, proving that our very experience of the world is a holistic construction. We see this same integrative power at work in the natural world within every ecosystem. A tropical rainforest is far more than just a collection of trees, insects, birds, and fungi. It is a single, breathing, interacting entity. The trees release water vapor that helps form clouds and generates its own rainfall. The fungal networks underground, the mycorrhizal web, connect the roots of trees, allowing them to share nutrients and warning signals. A change in one part of this system, the introduction of an invasive species or the removal of a key predator, ripples through the entire web in ways that are incredibly difficult to forecast. The health of the forest is a property of the whole system, not of any individual species. Its resilience, its ability to regulate climate, and its breathtaking biodiversity are all emergent, holistic qualities that could never be predicted by studying a single tree in a lab. The ecosystem behaves as a coherent unit. This holistic view does not seek to replace reductionism, it seeks to complement it. Reductionism is like using a magnifying glass to study the individual threads of a magnificent tapestry. It tells you about the material, the dye, and the weave. Holism is like stepping back to see the entire tapestry. It reveals the picture, the story, and the emotion that those threads collectively create. Both perspectives are essential for a complete understanding. You need to understand the physics of sound waves to appreciate a violin, but you need to hear the orchestra to experience Beethoven's Ninth Symphony. The reductionist approach gives us the how, the mechanics. The holistic approach gives us the why, the meaning, and the context. Now, let's scale this idea up to a truly cosmic level. We've already talked about galaxies as collections of stars, but a galaxy is also a holistic entity. The Milky Way doesn't just contain stars, it has an overall rotation, a specific shape with spiral arms, a magnetic field, and a life cycle. It behaves as a single system. Its future evolution is determined by the complex gravitational dance of all its components: stars, gas, dark matter, and the central supermassive black hole, all interacting as one. You cannot predict the motion of our solar system around the galactic center by only calculating the pull of the nearest star. You have to consider the gravitational field of the entire galaxy. It is a holistic gravitational entity, and this scales up even further to galaxy clusters and the vast cosmic web itself. These are not just random scattershots of objects. They are cohesive structures with their own dynamics, their own anatomy, and their own history. The universe builds itself into these larger and larger integrated wholes, each level exhibiting new and unexpected properties. This shift in perspective, from the isolated part to the integrated whole, invites us to see the entire cosmos not as a lonely collection of separate objects drifting in a void, but as a single, unified, and deeply interconnected system. Every particle, every planet, every star is a participant in this grand whole. Your body is a holism of 50 trillion cells working in concert. That body is part of the holism of a society, which is part of the holism of a planetary ecosystem, which is part of the holism of a solar system, and so on, all the way up. There are no truly separate things. There are only temporary patterns in an endless web of relationships. Recognizing this deep, integrative power of the universe allows us to appreciate that we are not just observers of the cosmos. We are expressions of it, inseparable from the whole and contributing in our own small way to its magnificent, unfolding story. But just as our universe reveals its intricate structure through interconnected networks and holistic systems, it also unfolds its grandest story across the deepest dimension of all, time itself. This brings us to the sweeping principle of temporal dynamics, the study of how complex systems don't just exist in a static state, but actively evolve and transform over deep time, their pathways sculpted by an intricate dance between immutable law, historical accident, and sheer random chance. Think of the cosmos not as a frozen snapshot, but as an epic, multi-billion-year movie, where every frame is shaped by the frames that came before it. The universe's incredible capacity for self-organization is not an instantaneous event. It is a chronological saga, a narrative written in the language of change, where the opening lines, the initial conditions, and every unexpected plot twist along the way forever steer the development of everything that follows. This profound influence of history is captured in the powerful concept of path dependence. Imagine walking through a fresh field of snow after a storm. Your first few steps are difficult. You have to compact the snow to create a path. But once that initial trail is blazed, it becomes the easiest route to follow. With every subsequent trip, the path becomes more deeply worn in, making all other potential routes across the field increasingly less likely to be taken. The options for your journey become constrained by the very first, almost random choice of where you placed your foot. This is path dependence in action, and we see it etched across the cosmos. The formation of our own Milky Way galaxy was a path-dependent process. The specific distribution of dark matter and the tiny quantum fluctuations in the early universe created a unique gravitational landscape. Once the first stars began to form in certain overdense regions, they attracted more gas and triggered further star formation, carving out the specific spiral structure we see today. That initial gravitational topography set our galaxy on a specific evolutionary path, one that would have been subtly different if even one of those primordial quantum dice rolls had landed another way, forever altering the story of our celestial home. We can witness this same interplay of chance and necessity in the grand story of life on Earth through the science of phylogenetics, which maps the evolutionary relationships between species. The magnificent diversity of life from the hummingbird to the blue whale is not the result of a predetermined linear plan. It is a sprawling, branching tree of possibilities, a narrative shaped by a series of historical contingencies. The asteroid impact that wiped out the dinosaurs was a random, catastrophic event from the perspective of a Tyrannosaurus rex. But for our small mammalian ancestors, it was an opportunity that opened an entirely new evolutionary pathway. That chance perturbation reset the board, allowing our lineage to diversify and eventually evolve complex cognition. Our existence is a testament to a specific, winding path through evolutionary time, a path that could have easily been foreclosed by a different throw of the cosmic dice. The fossil record is a history book filled with these forks in the road, showing us that evolution is not a march toward perfection, but a story of adaptation to countless unpredictable circumstances. This narrative of cosmic evolution is not driven by destiny, but is profoundly sensitive to its starting point, an idea famously illustrated by the butterfly effect in chaos theory. In the climate system, the flapping of a butterfly's wings in Brazil could theoretically set off a chain of escalating atmospheric events that ultimately influences the formation of a tornado in Texas weeks later. The flap itself doesn't cause the tornado, but it can be the tiny initial nudge that pushes a complex, nonlinear system down one path instead of another. We can scale this concept up to the origin of everything. In the first fleeting moments after the Big Bang, the universe was a seething quantum foam, a realm of fundamental uncertainty. Microscopic quantum fluctuations, random, unpredictable events at the smallest possible scale, were happening everywhere. The theory of cosmic inflation proposes that the violent exponential expansion of the universe stretched these quantum wrinkles to astronomical sizes. Those infinitesimal seeds of randomness became the gravitational wells that, over billions of years, attracted matter and grew into the vast cosmic web of galaxy clusters and immense voids we observe today. The entire large-scale structure of our universe may be a frozen monument to quantum chance, a permanent structure built upon a foundation of microscopic randomness, showing that the universe's story is written with a pen that occasionally splatters ink in wonderfully unexpected ways. Understanding these temporal dynamics allows us to see cosmic history not as a dry sequence of events, but as a rich, unfolding story. A narrative of creation where time is the essential medium. The universe is not a static object but a dynamic process, a verb rather than a noun. It is always becoming, always transforming. The laws of physics provide the grammar and the syntax, the rules of the game, but chance and history provide the plot twists and the characters. The initial conditions of the Big Bang set the stage. The fundamental constants provided the laws of interaction, and from that point on, the story began to write itself through a billion local interactions, each one opening some doors and closing others. From the forging of the first atoms to the birth of the first stars, from the assembly of planets to the spark of life, each new chapter built upon the last, layering complexity upon complexity in an irreversible journey. This perspective transforms our place within the cosmos. We are not merely inhabitants of a finished universe. We are living participants in an ongoing, creative epic, a single thread in a grand temporal tapestry that is still being woven, our own story inextricably linked to the deep time narrative that began some 13.8 billion years ago. Yet even as the universe unfolds its grand narrative across the deep river of time, its most profound acts of creation often occur not in wide open spaces, but at the very edges of things, in the places where one state of being meets another. This brings us to a principle that celebrates the creative power of limits themselves, the profound influence of boundary conditions, and the transformative magic of liminal spaces. We often think of boundaries as simple lines of separation, as limits that say, you can go no further. But in the cosmos, boundaries are not the end of the story. They are where the story gets truly interesting. They are the dynamic interfaces where different realities meet, interact, and cross-pollinate. becoming the most fertile ground in the entire universe for novelty, innovation, and the emergence of entirely new forms of complexity. We can start by considering the most fundamental boundary condition of all, the initial conditions of the universe itself. The Big Bang was not just a beginning, it was a setting of the cosmic stage, the establishment of a specific set of starting parameters that would forever guide and constrain everything that followed. The exact value of the density of matter and energy in that first moment, the precise ratio of particles to antiparticles, the specific rate of expansion, these were not arbitrary. They were the ultimate boundary conditions, the foundational rules written into the fabric of spacetime that would determine whether the universe would immediately collapse back on itself, fly apart into a thin haze, or take the precise, narrow path that allowed for galaxies, stars, and life to eventually form. The entire 13.8 billion-year history of cosmic evolution is the playing out of a story whose plot was deeply shaped by its very first sentence. Without those specific initial constraints, the elaborate self-organization we see everywhere would never have gotten off the ground. Now, fast forward billions of years, and we find another type of boundary that is equally mysterious and powerful: the event horizon of a black hole. This is not a physical surface you could touch. It is a mathematical boundary in space, a point of no return. Once matter or light crosses this threshold, it is forever lost to our observable universe, its information seemingly erased from our reality. This boundary condition creates one of the most extreme environments imaginable. Just outside the event horizon, in a region of unimaginable gravitational and tidal forces, particles are accelerated to near light speed, and magnetic fields become incredibly powerful. This chaotic, energetic interface is where black holes can power some of the most energetic phenomena in the cosmos, like quasars, which can outshine entire galaxies. The event horizon is a boundary that hides profound mysteries. What happens to the information of what falls in? Does it truly vanish? While simultaneously acting as a powerful engine that shapes the growth of galaxies and distributes energy throughout the cosmos, proving that even the most absolute of limits can be sources of immense creative influence. But you don't need to look to the edge of a black hole to see this principle in action. You can find it in the very building blocks of life. Every living cell on Earth is a masterpiece of boundary-defined existence. The cell membrane is not just a simple wall. It is a highly sophisticated and dynamic interface, a selectively permeable barrier that meticulously regulates what enters and exits. It maintains a stable internal environment that is radically different from the outside world, allowing the incredibly complex chemistry of life to proceed in a protected space. But it is far from a closed border. This boundary is bustling with activity. It is studded with intricate protein channels and pumps that act like customs agents, actively importing nutrients, exporting waste, and receiving signals from other cells. The cell membrane is the ultimate liminal space. It is the place where the self ends and the other begins. And it is precisely at this interface that the cell defines its identity and engages in the constant exchange that sustains its existence. Life itself began when a self-organizing set of chemical reactions became encapsulated within a primitive lipid membrane, creating the first protected pocket of order against the chaotic outside world. The boundary didn't stifle life, it made it possible. This creative power of edges is a well-known and celebrated phenomenon in ecology, in the zones known as ecotones. An ecotone is the transitional area between two adjacent ecological communities, like where a dense forest meets an open grassland, or where a river estuary blends fresh water with the salt water of the ocean. To a casual observer, these might seem like mere borders, but to an ecologist, they are the most biodiverse and dynamically active places in the entire landscape. The forest edge gets more sunlight than the deep woods, supporting a different set of plants that can't thrive in full shade or full sun. This, in turn, attracts a unique mix of animals from both habitats, grazers from the grassland and browsers from the forest, along with edge-specific species that specialize in this blended environment. The estuary, a boundary between river and sea, is a nutrient-rich soup where the mixing of waters creates an incredibly productive nursery for fish and a feeding ground for birds. The boundary is not a barren line. It is a rich seam of creativity where the overlapping influences of two different worlds generate an explosion of new possibilities and interactions. This concept is not just observed in nature. It is formalized in the language of mathematics through boundary value problems. Physicists and engineers use these mathematical tools to predict how a system will behave. You can't solve the equations for how heat will diffuse through a metal rod, for example, without first defining the boundary conditions. What is the temperature at each end of the rod? Is it insulated or exposed? The solution to the entire problem is completely dependent on the constraints you set at the edges. The boundaries don't just limit the solution, they define it. In a very real way, the beautiful, predictable equations that describe waves, heat flow, and quantum particles are all conversations between a system's internal dynamics and the specific conditions imposed at its borders. The universe itself seems to solve its physical equations in this way, with the properties of the whole emerging from the specific rules enforced at the interfaces. This brings us to the beautiful human concept of the liminal space, a term derived from the Latin word limen, meaning threshold. In anthropology and psychology, liminal spaces are those transitional periods of time, the in-between moments when we have left one state of being but have not yet arrived at the next. Think of the threshold of a doorway, the experience of adolescence, or the quiet, reflective time after a major life event has ended but before a new chapter has begun. These are often periods of uncertainty, but they are also periods of tremendous potential, creativity, and transformation. Old structures and identities are broken down, making room for new ways of being to emerge. The universe, in its endless creativity, seems to operate on this same principle. The most dramatic phase transitions, like water turning to steam or the early universe cooling to form atoms, occur in these liminal zones between states. It is in these turbulent, in-between places that the old rules break down and new orders are born. The universe doesn't build its complexity in the safety of the center. It builds it at the frontiers, on the edges, in the thrilling and uncertain spaces between what was and what will be. Recognizing this allows us to see limits not as barriers to our curiosity, but as the very catalysts for cosmic creativity, the places where the future is forged. But if the universe builds itself through dynamic interactions at boundaries and across time, perhaps its most astonishing act of construction is the emergence of something that can turn around and observe the entire process, a capacity that loops back on itself to ask, "What am I, and how did I get here?" This brings us to a principle that sits at the fascinating frontier of science and philosophy, the idea of reflexivity, the extraordinary ability of a system to not just exist, but to observe itself, to form a model of its own functioning, and to use that knowledge to consciously steer its own future. It's the difference between a river simply flowing down a mountain and a river that holds a mirror up to itself, sees its own course, and decides to carve a new path. This isn't just a human trait. It appears to be a latent potential woven into the fabric of a self-organizing universe, a final meta-layer of complexity where the cosmos begins to know itself. We are, of course, the most intimate example of this principle. Human consciousness is the universe's most sophisticated known experiment in reflexivity. Your brain is a physical system, a network of billions of neurons governed by the laws of physics and chemistry. But it has also generated something unprecedented, a subjective experience, a sense of self, an inner world that can observe and reflect upon the very brain that creates it. This loop of self-awareness is what allows us to do something no other animal can do to the same degree. We can run mental simulations of the future. We can imagine different outcomes based on different choices, reflect on past mistakes, and consciously plan long-term strategies for survival and flourishing. This reflexive capacity supercharges our ability to self-organize. A society isn't just a collection of people following instincts. It's a collective that creates laws, art, science, and ethics, all products of its ability to observe its own behavior and deliberately aim for a better, more organized state. Our entire civilization is a testament to the power of a system that has learned to think about itself. This concept of a system using self-modeling to guide its actions is no longer confined to biology. We are actively engineering it in the field of artificial intelligence. The most advanced AI systems aren't just passive tools following pre-written code. They are increasingly reflexive. A machine learning algorithm can be designed to monitor its own performance metrics. It can identify when its predictions are becoming less accurate, diagnose the reason for the drift, perhaps the data it's receiving has changed, and then retrain itself on new data to correct its course. It's a simple form of technological self-awareness, a feedback loop where the system observes its own output and uses that information to adjust its internal processes. This reflexivity is what makes modern AI so powerful and adaptable. It's a rudimentary form of the same principle that allows us to learn from experience, suggesting that reflexivity might be a natural endpoint for sufficiently complex information processing systems, whether they are made of carbon or silicon. This idea becomes truly mind-bending when we scale it up to the universe itself and consider the profound role of observation in quantum mechanics. In the quantum world, a particle does not have definite properties, like a specific position or spin, until it is measured. Before measurement, it exists in a fuzzy cloud of potentialities, a superposition of all possible states. The very act of observation, the interaction between the quantum system and a measuring device, seems to force it to choose a single, definite reality. This is the famous measurement problem, and it suggests a deep, reflexive relationship between the observer and the observed. The physicist John Wheeler took this idea to its ultimate conclusion with his concept of the participatory universe. He proposed that we are not just passive observers of a pre-existing cosmos. Through the act of observation, particularly events that look back to the beginning of time, we somehow participate in bringing the universe into being. In his delayed choice thought experiments, a decision made by an observer in the present appears to influence the path a photon took billions of years ago. It's as if the universe requires a conscious witness to solidify its own history, a breathtakingly reflexive loop where the present helps create the past. This perspective invites a radical, almost poetic, possibility that the universe's long journey of self-organization, from the Big Bang to galaxies, stars, planets, and life, might have a direction. Perhaps it is all an elaborate, billion-year process aimed at eventually creating pockets of self-awareness observers that can reflect the cosmos back onto itself, completing a grand loop of existence. In this view, a star is not just a fusion reactor. It is a factory forging the carbon atoms necessary for life. A galaxy is not just a collection of stars. It is an island universe providing the stable billions of years needed for planets to evolve conscious beings. We are not just accidents in a meaningless void. We are the universe's way of becoming aware of its own beauty, its own structure, and its own laws. This doesn't require a mystical life force. It simply requires that the laws of physics allow for complexity to increase to the point where reflexivity emerges naturally. We are a part of the universe, and we are awake. And in our awakening, the universe, in a very real sense, awakens to itself. And so we arrive at a principle that feels almost like a beautiful, culminating symphony, a grand finale that weaves together every thread we've explored. After journeying through the universe's love of chaos, its reliance on stable laws, its building through both competition and collaboration, we now see how it masterfully unites all these forces into a single, breathtaking whole. This is the principle of unity in diversity, the cosmic harmony that emerges when a near-infinite variety of forms and forces find a way to cooperate, creating a cohesive and dynamic reality that is both stable and bursting with innovation. It's the universe's ultimate demonstration that you don't need to choose between sameness and difference. The most profound order arises from their exquisite and delicate balance. We can hear this principle played out in the most fundamental language of reality, the standard model of particle physics. This is the incredible theoretical framework that catalogs the known fundamental particles and three of the fundamental forces that govern them. At first glance, it seems like a menagerie of bewildering diversity. You have the familiar electrons, the up and down quarks that make up protons and neutrons, and the photon that carries light. But then you have the stranger cousins, the muon and the tau, the charm and strange quarks, and a whole zoo of neutrinos. Each has its own unique mass, charge, and role to play. They are the diverse instruments in the cosmic orchestra. But what creates the harmony? The underlying, unifying laws that govern them all. Every single one of these wildly different particles obeys the same quantum rules, the same principles of symmetry, and the same conservation laws. Their interactions are dictated by a beautiful, mathematical consistency. The diversity of the parts is made possible by the profound unity of the underlying rules. Without this unity, the particles would be a chaotic, lawless soup. Without the diversity, the universe would be a featureless void, incapable of building atoms, molecules, or minds. This beautiful interplay between the one and the many is echoed in the largest structure we know of, the cosmic web. When we map the universe in 3 dimensions, we don't see a random scattering of galaxies. We see an intricate architecture of dense clusters, long, delicate filaments, and vast, empty voids. It is a structure of breathtaking variety, a tapestry of light and shadow on an unimaginable scale. Yet, this entire web, in all its complexity, emerged from a single, unified process, the gravitational attraction of matter, both dark and visible, acting on the tiny quantum fluctuations imprinted in the first moments of the Big Bang. One simple, universal force, gravity, acting on one set of initial conditions, gave rise to this spectacularly diverse and intricate pattern. The unity of the law created the diversity of the structure. And within that structure, the galaxies themselves, though islands of stars, are not isolated. They are connected by the gravitational pull of the filaments, influencing each other's rotation and evolution. The diverse nodes and the unifying connections work together to create a stable, yet evolving, cosmic ecosystem. We can find a perfect metaphor for this in the world of music. A single, pure musical note played on a flute is beautiful in its simplicity, but it is limited. Now, bring in a cello playing a different note, and a violin playing another. Each instrument contributes its own unique voice, its own frequency, its own timbre. This is the diversity. But when these different notes are played together in relation to a fundamental key or chord, they don't create noise, they create harmony. The chord is a new, emergent property that is more beautiful and complex than any single note within it. The unity of the musical scale and the rules of harmony are what allow this diversity of sounds to coalesce into something coherent and emotionally powerful. A symphony orchestra is the ultimate expression of this. Hundreds of different musicians, each mastering a different instrument, all reading from the same sheet of music, following the same conductor, to create a unified artistic expression that could never be achieved by any one player alone. This is precisely how a healthy ecosystem functions. A tropical rainforest thrives on its incredible biodiversity, thousands of species of plants, insects, birds, and mammals, all occupying different niches. Some animals pollinate flowers, others disperse seeds, and others break down decaying matter. This diversity is not chaotic. It creates resilience and stability. If a disease wipes out one species, another can often fill its ecological role, preventing the entire system from collapsing. The unity comes from the shared environment and the interconnected food webs that bind all these lives together. Each organism, in pursuing its own survival, inadvertently contributes to the health and balance of the whole. The ecosystem is a self-organizing whole that leverages diversity to create a robust and harmonious unity, a dynamic equilibrium that can adapt to change and endure through time. This cosmic dance between uniformity and innovation is ultimately made possible by the precise calibration of the fundamental constants of nature. These are the universal rules, the deep-level unity that allows for such surface-level diversity. The strength of gravity, the mass of an electron, the force that binds atomic nuclei, these values are exquisitely fine-tuned. If they were even slightly different, the universe would be a very dull place. Too strong a gravitational constant, and the universe would have collapsed immediately after the Big Bang. Too weak, and no galaxies or stars could ever form. These constants provide the stable, uniform foundation, the consistent rules of the game. Within the safe playing field defined by these unifying rules, the universe is then free to explore near-infinite possibilities, to form 100 billion different galaxies, each with hundreds of billions of stars, and around those stars, a staggering variety of planets and perhaps life forms. The unity of the laws guarantees the stability of the whole, while simultaneously enabling an endless frontier of novelty and diversity within that whole. Imagine the cosmos as a magnificent tapestry, vast beyond comprehension. Every thread in this tapestry is different. Some are the deep red of a giant star, others the cool blue of a gas giant, still others the vibrant green of a forested planet. There are threads of dark matter, invisible but essential to the structure, and threads of conscious thought, tiny but brilliant. Individually, each thread has its own story, its own unique properties. But woven together on the loom of physical law, they create a single, breathtaking image, a picture of a universe that is interconnected, coherent, and whole. The beauty of the tapestry does not lie in any single thread, but in their harmonious integration. The universe builds itself not through conformity, but through a glorious and dynamic dance of sameness and difference, where the unwavering constancy of its laws provides the stage for an endless, creative explosion of form and phenomenon, resulting in a reality that is both deeply ordered and wonderfully wild. As we've journeyed together through the self-organizing patterns of the universe, from the elegant dance of symmetry, breaking to the infinitely repeating tapestry of fractal geometries, we've witnessed a reality that constructs itself not through random accident, but with profound elegance and deep intention. These 26 principles, from the guiding hand of invariance to the creative spark of perturbation, weave together to form a single, breathtaking picture, a cosmos that is fundamentally ordered, building staggering complexity from stunning simplicity through a set of timeless, universal rules. This isn't a universe that simply happened. It is a universe that continually happens, an active, ongoing process of becoming where order emerges from chaos, patterns crystallize from noise, and beauty arises from the relentless application of a few deep physical laws. This understanding completely transforms our place within this grand cosmic story. We are not merely passive observers, distant spectators on a lonely rock spinning through an indifferent void. We are active participants, deeply embedded in the very fabric of this self-constructing reality. The calcium in our bones was forged in the heart of a long-dead star, a product of stellar autocatalysis. The neural networks in our brains, which allow us to even comprehend these ideas, are a magnificent example of emergent complexity, a living testament to the universe's capacity for self-awareness. Every time we learn, create, or form a new connection with another person, we are engaging in the same fundamental processes that shape galaxies and fold proteins. We are the universe, consciously awakening to itself, and in our acts of creation and community, we are continuing the great work of cosmic construction right here, right now. I would love to hear how this perspective resonates with you. Down in the comments, tell me about the patterns you've noticed in your own life. The fractal branching of a tree outside your window, the synchronized flow of traffic on a highway, or the way a simple idea can ripple through a community and create unexpected change. Your observations are part of this story too. If this deep dive into the mysteries of a self-building cosmos has sparked your curiosity, please consider subscribing to the channel for more journeys to the edges of our understanding. And as you go about your day, remember this: the universe is not a finished product. It is a verb, not a noun. It is always building, always evolving, always discovering new forms of order. And so are we. Thank you for joining me on this exploration. Keep questioning, keep wondering, and as always,